Imagine discovering a civilization through the things it never explained. Across the ancient world stand monuments that outlived their creators by thousands of years, yet many still refuse to reveal how or why they were built. Some were carved directly into solid rock, others assembled from stones so enormous they seem impossible to move with ancient technology. Their geometry is astonishing, their durability extraordinary, and their purpose often uncertain. Each generation arrives with more advanced tools, yet the same questions remain. Instead of making the ancient world less mysterious, every new discovery seems to expose just how much of humanity's earliest knowledge has been lost. These are the places where archaeology ends, and the mystery truly begins. Perched on the southeastern coast of Santorini, Greece, ancient Thera clings to the steep summit of Mesa Vuno, nearly 400 meters above the Aegean Sea. More than 23 centuries after its foundation, an entire city still occupies the unstable slopes of an active volcanic island, where geology suggests many of its buildings should have collapsed long ago. The ruins remained largely forgotten after the Byzantine period, until systematic excavations began in 1895 under the direction of German archaeologist Friedrich Hiller von Geertringen, who uncovered an extensive urban settlement stretching across the mountain crest. What emerged was not simply another Greek city, but a remarkable example of ancient engineering built directly onto one of the most geologically hazardous landscapes in the eastern Mediterranean. The greatest mystery is not why ancient Thera was built here, but how its builders prevented an entire city from slowly sliding toward the sea. Mesa Vuno rises approximately 360 to 396 meters above sea level, with many natural slopes exceeding 30 degrees. Modern geotechnical engineering recognizes volcanic terrains of this kind as particularly vulnerable to rockfalls, erosion, and slope instability, because they consist of alternating layers of basalt, volcanic tuff, scoria, and weathered pyroclastic deposits that differ greatly in strength. On active volcanic islands, repeated earthquakes gradually weaken these layers, increasing the likelihood of large-scale slope failure over centuries. Yet instead of constructing on the relatively safer coastal plains, the inhabitants deliberately established their city high on the mountain and anchored virtually every street, temple, and house directly into the rock itself. More than 2,000 years later, large sections of those foundations still occupy their original positions, despite centuries of earthquakes, heavy winter rainfall, strong Aegean winds, and continuous weathering. Archaeologists have found no evidence of deep retaining piles, concrete foundations, or any comparable technology capable of stabilizing such a settlement by modern standards. Instead, the city appears to rely almost entirely on carefully cut bedrock, stepped terraces, and gravity alone. Exactly how ancient surveyors determined which portions of the volcanic mountain could safely support permanent construction remains one of the site's least understood engineering achievements. That remarkable stability becomes even more surprising when examining how the city interacted with the terrain instead of attempting to reshape it. Rather than leveling the summit into broad platforms, the builders carved hundreds of narrow terraces that closely followed the natural contours of the mountain. Every terrace reduced the downhill forces acting upon the structures above, while transferring weight directly into competent bedrock. Modern slope engineering frequently employs terracing to decrease soil movement and distribute structural loads. Yet ancient Thera achieved similar results more than 2 millennia before the mathematical principles governing slope stability were understood. The surviving terraces continue to preserve their geometry despite thousands of seasonal cycles of expansion, contraction, and erosion. No written records explain how builders determined terrace dimensions, spacing, or foundation depths, leaving their practical knowledge almost entirely lost. The walls themselves introduce another puzzle. Much of ancient Thera was constructed using dry stone masonry, where carefully shaped blocks were fitted together without mortar. Conventional logic suggests that mortar strengthens masonry by locking stones into a rigid mass, yet rigid walls often perform poorly during earthquakes because they cannot accommodate ground movement. Dry masonry behaves differently. Slight movement between individual stones allows seismic energy to dissipate instead of concentrating stress within a single fracture. Modern earthquake engineering recognizes controlled flexibility as an effective strategy for improving structural resilience, but the extent to which ancient Thera's builders intentionally exploited this behavior remains uncertain. The remarkable survival of numerous wall segments after centuries of seismic activity suggests they may have understood practical principles that were never recorded in surviving Greek technical literature. The foundations reveal another level of sophistication. Instead of placing buildings upon prepared soil, masons frequently cut shallow channels directly into solid volcanic rock before laying the first course of masonry. This approach effectively integrated each structure with the mountain itself, greatly reducing differential settlement that commonly develops when buildings rest on loose sediments. Even today, anchoring structures into competent bedrock remains one of the most reliable methods of stabilizing construction in mountainous regions. What remains unknown is how ancient builders identified the strongest portions of the volcanic substrate without geological mapping, drilling equipment, or laboratory analysis. Neighboring outcrops formed by different eruptions can possess dramatically different fracture densities and weathering resistance, despite appearing nearly identical on the surface. Water presented an equally serious threat to the city's survival. On steep volcanic slopes, uncontrolled runoff can rapidly erode supporting material beneath foundations, triggering landslides that destroy entire settlements. Excavations throughout ancient Thera have uncovered an integrated network of stone channels, drains, and carefully graded streets that diverted rainwater across multiple routes instead of allowing concentrated torrents to flow downhill. By dispersing runoff before it gathered destructive energy, the system reduced erosion beneath critical foundations. Modern hydraulic engineers describe similar strategies as energy dissipation and distributed drainage. Yet there is no surviving description explaining how ancient planners calculated gradients or anticipated seasonal water volumes on such difficult terrain. The choice of building stone also appears unusually deliberate. Santorini experiences constant exposure to salt-laden winds, intense solar radiation, and rapid temperature fluctuations that accelerate physical weathering. Not every volcanic rock responds equally under these conditions. Geological studies show that differences in porosity, mineral composition, and internal fracturing strongly influence long-term durability. Many buildings at ancient Thera appear concentrated on more competent volcanic bedrock, while avoiding weaker weathered deposits wherever possible. The surviving masonry suggests that builders may have distinguished subtle variations in rock quality long before geology existed as a scientific discipline, although the observational methods they used disappeared with the civilization itself. The broader geological setting makes this achievement even more extraordinary. Santorini forms part of the Hellenic volcanic arc, one of Europe's most active volcanic regions, where tectonic interaction between the African and Eurasian plates continues to generate earthquakes and volcanic unrest. Although the catastrophic Late Bronze Age eruption occurred centuries before ancient Thera was founded, the island remained tectonically active throughout the city's existence. Historical records and modern seismic monitoring confirm that the region has experienced repeated destructive earthquakes over the last 2,000 years. Yet significant portions of the city's street grid, terraces, retaining walls, and foundations remain recognizable today. Their continued survival reflects far more than durable stone alone. It represents thousands of individual engineering decisions concerning geology, drainage, structural loading, and terrain management that consistently favored long-term stability. Perched above the city of Cusco in the Peruvian Andes at an elevation of approximately 3,700 meters, Sacsayhuaman is a fortress whose massive stone walls appear to defy one of nature's most destructive forces. More than 5 centuries after the arrival of the Spanish, and despite repeated powerful earthquakes in one of South America's most active seismic regions, its towering terraces remain standing where many younger structures have repeatedly failed. Unlike Machu Picchu, Sacsayhuaman was never truly lost. Spanish chroniclers, including Pedro Cieza de León, described the fortress shortly after the conquest of the Inca Empire in the 16th century, although much of its finely cut stone was later dismantled and reused to construct colonial buildings throughout Cusco. Even after centuries of quarrying, enough of the original structure survived for archaeologists and engineers to recognize that the remaining walls represented one of the most extraordinary examples of prehistoric stone engineering ever built. The greatest mystery is not how large the stones are, but why the walls have refused to collapse. Cusco lies within the active Andean seismic belt, created by the ongoing subduction of the Nazca Plate beneath the South American Plate, a tectonic process occurring at roughly 7 to 8 centimeters per year. This region has experienced numerous destructive earthquakes throughout recorded history, including major events in 1650, 1950, and many smaller earthquakes that continuously subject ancient structures to repeated cycles of ground motion. Colonial churches, masonry buildings bonded with mortar, and later stone constructions have all suffered severe damage or complete collapse during these events. Yet the polygonal walls of Sacsayhuaman remain remarkably intact. For structural engineers, this represents the site's most remarkable achievement, because the walls appear to survive precisely by doing what conventional masonry should never do. Instead of resisting earthquakes as rigid bodies, they seem to move with them. Modern structural analyses suggest that each stone functions as an independent structural element, capable of minute movement during seismic shaking. Rather than transferring stress directly through continuous mortar joints, the dry-fitted blocks distribute seismic energy across hundreds of irregular contact surfaces. Small displacements measured in millimeters allow the blocks to absorb energy before gravity guides them back into position once the shaking subsides. This principle resembles modern seismic isolation concepts, although it was achieved entirely through geometry rather than engineered bearings or synthetic materials. Numerical modeling published by engineering researchers has shown that irregular polygonal joints reduce stress concentrations that normally develop along straight vertical mortar seams, making crack propagation significantly more difficult during cyclic loading. Whether Inca builders fully understood these mechanical principles remains impossible to prove, yet the performance of the walls over centuries strongly suggests an empirical mastery of earthquake-resistant construction unmatched anywhere else in the pre-Columbian Americas. The geometry of the masonry only deepens the mystery. Unlike conventional walls built from standardized rectangular blocks, almost every visible stone at Sacsayhuaman possesses a completely unique outline. Many blocks contain 10, 12, or even more than 15 precisely shaped faces that interlock with neighboring stones in multiple directions simultaneously. The contact surfaces are so accurately fitted that even today many joints remain only a few millimeters wide, despite centuries of weathering. The fortress was primarily constructed from extremely hard andesite, an igneous rock considerably more difficult to shape than the limestone used for many ancient monuments elsewhere. Experimental archaeology has demonstrated that andesite can be worked using harder stone hammers and abrasive techniques, yet reproducing the same level of precision across hundreds of irregular multi-ton blocks remains extraordinarily labor-intensive. No surviving Inca documents explain how templates, measurements, or fitting sequences were organized, leaving the entire production process largely reconstructed through inference rather than direct evidence. The enormous size of the stones creates another engineering puzzle. The largest surviving blocks are commonly estimated to weigh between 100 and 150 tons, while some researchers have proposed values approaching 200 tons for the largest examples depending on volume calculations and rock density. These stones stand on steep mountain terrain without reinforced concrete foundations, steel anchors, or deep piles. Geological surveys indicate that many sections were placed directly upon carefully prepared natural bedrock rather than artificial platforms. By anchoring the walls to stable rock instead of relying on thick masonry foundations, Inca engineers reduced differential settlement while allowing the structure to behave as part of the underlying mountain itself. The result is a foundation system that has remained stable despite centuries of seismic activity and seasonal environmental change. The famous zigzag layout of the three defensive terraces may also represent more than military architecture. Historians traditionally interpret the repeated angles as a method for creating overlapping defensive positions from which defenders could attack advancing enemies from multiple directions. Structural engineers, however, have proposed that the constantly changing wall orientation may provide an additional mechanical benefit. Long, uninterrupted walls tend to transmit seismic forces continuously along their entire length, whereas repeated changes in direction interrupt stress paths and distribute loads into multiple segments. Although this hypothesis remains under investigation, finite element simulations indicate that irregular geometry can reduce localized concentrations of force, raising the possibility that defensive planning and structural resilience were achieved simultaneously through the same architectural design. Even the connections hidden within the walls continue to generate debate. Detailed surveys have revealed that many stones are not merely pressed together across flat surfaces. Instead, some incorporate subtle projections, recesses, and three-dimensional interlocking features that prevent individual blocks from sliding independently. Removing a single stone would often require moving several neighboring blocks first, because the entire assembly behaves as a mechanically integrated system rather than a stack of separate components. Since much of this internal geometry remains concealed beneath adjoining stones, researchers cannot fully reconstruct the complete locking mechanism without dismantling the monument itself, something that preservation efforts rightly prohibit. Transporting the stones from nearby quarries remains one of the least understood stages of construction. Most of the andesite originated several kilometers from the fortress, requiring enormous blocks to be moved across uneven mountain terrain at nearly 3,700 meters above sea level. The Inca possessed no iron tools, no wheeled vehicles capable of hauling such loads, and no large draft animals comparable to horses or oxen. Experimental studies suggest that hundreds of workers using braided fiber ropes, wooden rollers or sledges, earthen ramps, and carefully coordinated labor could theoretically move extremely heavy stones. Yet no experiment has successfully reproduced the transportation and final placement of the largest blocks under authentic Andean conditions, leaving significant uncertainty regarding the exact construction sequence. Perhaps the strongest evidence of Sacsayhuaman's engineering achievement lies not in speculation, but in history itself. During the major earthquakes that struck colonial Cusco, countless Spanish buildings constructed with stone and mortar cracked or collapsed entirely, while many of the Inca walls at Sacsayhuaman remained standing with only minimal displacement. The contrast became so striking that Spanish builders eventually reused Inca foundations as the structural bases for churches and government buildings, having learned through experience that Inca construction techniques often performed better than their own. Petra lies among the sandstone mountains of southern Jordan, appearing like a city that should have vanished long ago. Yet more than 2,000 years after its construction, enormous monuments carved directly into fragile cliffs continue to stand in one of the Middle East's most geologically active and erosive landscapes. The greatest mystery is not who built Petra, but why so much of it still exists. Although local Bedouin communities always knew of the site, Petra remained largely unknown to the outside world until 1812, when Swiss explorer Johann Ludwig Burckhardt reached the hidden city by disguising himself as an Arab traveler. What he revealed was not simply an abandoned capital of the Nabatean kingdom, but one of the largest rock-cut engineering achievements ever created. UNESCO estimates that hundreds of monuments, temples, tombs, water systems, and public buildings were carved directly into the surrounding mountains between approximately the 4th century BCE and the 2nd century CE. Since then, archaeologists, structural engineers, and geologists have continued to study Petra, yet many of its most remarkable engineering decisions remain only partially understood. Nothing demonstrates this better than Al-Khazna, better known as the Treasury. Rising approximately 40 meters high and 25 meters wide, its entire facade was carved directly into a single vertical sandstone cliff, rather than assembled from individual stone blocks. Modern engineering immediately encounters an uncomfortable question. Every column, cornice, pediment, and sculptural element aligns with extraordinary precision, yet almost all archaeological evidence indicates that Nabatean craftsmen carved the monument from the top downward. This approach reduced the danger of falling debris damaging completed sections below, but it also meant that every measurement made near the summit determined the position of architectural elements dozens of meters beneath. A deviation of only a few centimeters at the beginning could have produced visible errors, exceeding tens of centimeters by the time the workers reached ground level. Despite this cumulative risk, laser surveys show remarkably consistent symmetry across the facade, with decorative elements maintaining proportional relationships comparable to those expected in carefully planned Hellenistic architecture. No construction drawings survive, no measuring instruments have been discovered, and no written Nabatean engineering manuals explain how surveyors transferred precise geometric layouts onto an irregular vertical cliff before excavation even began. The technical procedure behind one of the world's most famous facades therefore remains almost entirely invisible. The mystery deepens because the workers were not carving marble or granite, but sandstone, a material that presents entirely different structural problems. Petra's cliffs belong mainly to Cambrian and Ordovician sandstone formations, composed of layers with varying grain size, cementation, and fracture density. From a geological perspective, neighboring sections of the same cliff can possess dramatically different mechanical strength, despite appearing nearly identical from a distance. Selecting the wrong section could have resulted in large fractures propagating through finished monuments years or decades after excavation. Instead, many of Petra's largest facades remain attached to remarkably stable rock masses after more than 20 centuries. Geological investigations suggest that Nabatean builders repeatedly favored massive sandstone units with fewer discontinuities while avoiding heavily fractured zones whenever possible. Whether this selection resulted from systematic geological observation, practical quarrying experience, or another method entirely remains unknown because no contemporary explanation survives. Their apparent understanding of rock mechanics becomes even more surprising when considering Petra's environment. Unlike monuments protected inside caves, most famous facades remain fully exposed to sunlight, wind, rainfall, and daily temperature fluctuations. Sandstone expands and contracts as temperatures change, absorbs moisture during storms, and gradually weakens through salt crystallization and weathering. Under normal conditions, these processes slowly enlarge existing fractures until portions of a cliff detach. Petra has certainly suffered erosion, but the survival of many of its largest monuments exceeds what engineers once expected from exposed sandstone architecture of comparable age. Several researchers have suggested that the orientation of major facades, local microclimates within narrow valleys, and careful selection of more competent rock collectively slowed deterioration. Yet, the relative importance of each factor remains actively debated. The surrounding landscape introduces another engineering challenge that appears almost contradictory. Petra lies within an arid region, receiving relatively little annual rainfall, yet its greatest natural threat has never been drought alone, but sudden flash floods. The narrow entrance canyon, known as the Sick Funnels, run off from a watershed covering more than 90 square kilometers. During intense storms, enormous volumes of water can accelerate through passages only a few meters wide, transforming quiet walkways into destructive torrents capable of carrying boulders downstream. Modern visitors are occasionally evacuated because flash floods still threaten the archaeological site today. Long before modern hydrology existed, Nabatean engineers designed an integrated hydraulic network that fundamentally altered the behavior of these floodwaters. Dams diverted the strongest flows away from the city. Rock-cut channels intercepted runoff along canyon walls. Ceramic pipelines transported drinking water. Settling basins removed sediment. Reservoirs stored seasonal supplies, and hundreds of cisterns distributed water throughout the settlement. Archaeological surveys estimate that the entire hydraulic system extended for many kilometers across the surrounding mountains, allowing a large urban population to flourish in an environment that naturally could not have supported it. Without this infrastructure, Petra would likely have faced repeated catastrophic flooding, while simultaneously lacking reliable freshwater during dry seasons. Even within these hydraulic works, another unanswered question appears. Many water channels maintain remarkably consistent gradients, despite winding through irregular cliffs and narrow canyons. Hydraulic engineering requires slopes that are neither excessively steep nor nearly horizontal. Water flowing too rapidly erodes channels, while water moving too slowly deposits sediment that eventually blocks the system. Maintaining appropriate gradients across long distances normally requires accurate surveying instruments capable of measuring elevation differences with high precision. No definitive evidence has identified exactly how Nabatean engineers achieved these measurements across such difficult terrain, leaving their surveying methods largely speculative. Some channels also preserve waterproof coatings composed of lime-based plaster and ceramic materials that reduced water loss through the porous sandstone. These coatings endured repeated thermal expansion, seasonal flooding, and centuries of environmental exposure before gradually deteriorating. Analyses have improved understanding of their composition, yet the complete technological process that allowed these protective layers to remain effective for so long has not been fully reconstructed. Petra also occupies a region shaped by the Dead Sea Transform Fault System, one of the most significant tectonic boundaries in the Middle East. Historical records describe major earthquakes affecting the area in 363 CE, 551 CE, and 747 CE, with archaeological evidence confirming substantial destruction throughout the city. Temples collapsed, infrastructure failed, and parts of Petra were abandoned, yet some of its most recognizable monuments, including the treasury and the monastery, remained standing. One explanation is that carving monuments directly into the parent rock eliminated many structural weaknesses associated with freestanding masonry, allowing seismic forces to disperse through the surrounding cliff rather than concentrating along mortar joints. Even so, this principle alone does not fully explain why enormous freestanding columns, pediments, and deeply undercut decorative elements survived repeated seismic events while remaining attached to weathered sandstone cliffs. What do you think is Petra's greatest engineering mystery? Share your thoughts in the comments below. Machu Picchu remained unknown to the outside world until American historian Hiram Bingham reached the mountaintop in 1911 while exploring the Urubamba Valley of southern Peru. Perched approximately 2,430 meters above sea level on a narrow ridge between the peaks of Machu Picchu and Huayna Picchu, the Royal Inca estate was constructed around the middle of the 15th century during the reign of Emperor Pachacuti. Although local farming families had never completely forgotten its existence, systematic archaeological surveys, geological mapping, laser scanning, drone photogrammetry, and decades of engineering research transformed what first appeared to be an abandoned mountain city into one of the most remarkable examples of ancient structural engineering ever documented. Yet the greatest mystery is no longer who built Machu Picchu, but why a city standing on one of the most unstable mountain settings in the Andes has survived more than 5 centuries despite powerful earthquakes, nearly 2 meters of annual rainfall, landslides, and continuous weathering that should have destroyed it long ago. The answer becomes even more puzzling when modern geology reveals that Machu Picchu occupies a location most engineers would normally avoid. Geological investigations led by Brazilian geologist Rualdo Menegat demonstrated that the city sits directly on the intersection of several major fault systems, including the Machu Picchu, Huayna Picchu, and Urubamba faults, together with hundreds of smaller fractures cutting through the granite bedrock. Such environments are generally considered highly susceptible to rock instability because fault zones create planes of weakness that encourage landslides and amplify seismic movement. Building an entire city on top of this fractured mountain appears, at first glance, to have been an extraordinary mistake. Instead, evidence increasingly suggests the opposite. The Inca may have deliberately selected the site because the natural fracture network made quarrying easier, reduced the effort required to split enormous granite blocks, created natural drainage pathways for groundwater, and relieved internal rock stress before construction even began. Rather than fighting the mountain, they appear to have incorporated its geological weaknesses into the design itself, a decision that still challenges conventional assumptions about ancient engineering. That understanding naturally leads to another astonishing discovery hidden beneath the visible ruins. Visitors admire temples, terraces, stairways, and plazas, but archaeological excavations indicate that roughly 60% of Machu Picchu's construction lies underground. Beneath nearly every building extends a carefully engineered foundation consisting of successive layers of large stones, smaller rocks, gravel, coarse sand, and compacted soil. In many locations, these subsurface layers reach depths of 3 to 5 meters before reaching stable bedrock. Modern geotechnical engineers recognize exactly why such a system works. Each layer distributes structural loads differently, while allowing infiltrating rainwater to drain rapidly instead of accumulating beneath foundations, thereby reducing pore water pressure that often triggers slope failure. The remarkable question is not whether this system functions, because it clearly does, but how Inca builders determined the appropriate depth, composition, and sequence of these buried foundations centuries before soil mechanics became a scientific discipline. The importance of water management becomes impossible to ignore once the local climate is considered. Machu Picchu receives roughly 1,900 to more than 2,000 millimeters of rainfall each year, concentrated during intense wet seasons, capable of saturating steep Andean slopes within days. On an unprotected mountain ridge, such conditions normally produce erosion, mudslides, and progressive structural collapse. Yet, hydrological studies conducted by the right water engineers and later archaeological investigations identified an integrated drainage system unlike anything expected for a 15th century settlement. More than 120 stone-lined drainage outlets remain distributed throughout the city, connected to concealed channels, permeable foundations, and carefully graded plazas that continuously direct runoff away from buildings. Researchers estimate that nearly 80% of the engineering effort invested in Machu Picchu may have been devoted not to temples or palaces, but to controlling water. Even today, many drainage channels continue functioning almost exactly as intended, preventing standing water from accumulating despite centuries of seasonal storms. As rain disappeared safely into the mountain rather than collecting on its surface, another engineering solution quietly protected the city whenever earthquakes struck the Andes. Peru lies along one of Earth's most active convergent plate boundaries, where the Nazca Plate subducts beneath the South American Plate, generating frequent seismic activity. Historical earthquakes have repeatedly devastated colonial cities throughout the region, yet Machu Picchu suffered remarkably little structural failure. The explanation lies within the famous mortarless masonry perfected by Inca stonemasons. Massive granite blocks, some weighing more than 20 or even 50 tons, were shaped into irregular polygonal forms that fit together with extraordinary precision. Instead of relying on rigid mortar joints that crack under stress, the stones can shift by tiny fractions of a millimeter during seismic shaking before settling back into their original positions. Modern structural engineers often describe this behavior as a form of controlled rocking, allowing walls to dissipate seismic energy without catastrophic fracture. Laser measurements confirm that many joints remain exceptionally tight after hundreds of years of repeated earthquakes, demonstrating a level of seismic resilience that continues to inspire earthquake-resistant architecture today. Those walls could never have remained stable without solving an equally difficult problem surrounding the entire city. Approximately 170 agricultural terraces descend the mountain slopes below Machu Picchu, creating one of the most recognizable landscapes in South America. Although traditionally interpreted as farmland, engineering studies reveal that the terraces performed an equally critical structural function. Each retaining wall encloses multiple drainage layers consisting of large rocks, gravel, sand, and fertile topsoil arranged from bottom to top. Rainwater rapidly infiltrates these permeable layers before escaping through concealed outlets, preventing hydrostatic pressure from building behind retaining walls. This design dramatically reduces the risk of rotational landslides, one of the most common failure mechanisms affecting steep mountain slopes. Without this immense stabilization network surrounding the settlement, the mountain itself might gradually have slid toward the Urubamba River far below. Even after understanding the foundations, drainage, and terraces, another unresolved engineering question remains. The granite used throughout Machu Picchu originated locally, yet many individual blocks weigh between 20 and 50 tons, while the Inca possessed neither iron tools, wheeled vehicles, nor large draft animals capable of hauling such loads uphill. Experimental archaeology demonstrates that teams using ropes, wooden rollers, earthen ramps, and levers can transport heavy stones over limited distances, but no experiment has yet reproduced every stage of extraction, transportation, rotation, placement, and final fitting under the same mountainous conditions encountered at Machu Picchu. The extraordinary precision achieved on curved stone surfaces further complicates the problem because adjoining blocks frequently match along irregular three-dimensional contact faces that leave virtually no visible gaps. Although researchers generally agree on the broad principles involved, the complete construction sequence remains incompletely understood. The city's sophisticated understanding of hydraulics appears once again in its freshwater supply. Rather than depending on stored rainwater, the Inca intercepted a perennial spring emerging from fractured granite above the settlement. Engineers carved a canal approximately 750 meters long with a remarkably consistent gradient that maintained steady flow without causing erosion. Water then entered a sequence of 16 fountains, descending through the urban sector, supplying residences, ceremonial spaces, and agricultural areas, before safely rejoining the drainage network. Modern hydraulic analyses indicate that maintaining such a controlled gradient required careful surveying, because even slight deviations could either slow the flow enough to create sediment accumulation or accelerate it sufficiently to damage the channel. More than 5 centuries later, sections of this hydraulic system continue carrying water with only limited restoration. Ajanta caves remained hidden beneath dense jungle in the Sahyadri hills of Maharashtra, Western India, until British officer John Smith accidentally encountered the site while hunting in 1818. Cut into a horseshoe-shaped basalt cliff overlooking the Waghora River, the complex contains 30 rock-cut caves created between the 2nd century BCE and approximately the 6th century CE. At first glance, Ajanta appears to be another remarkable Buddhist sanctuary, yet modern geological surveys, laser documentation, structural analyses, and archaeological research reveal a far deeper engineering mystery. The greatest question is not who carved these monuments, but how an entire mountainside could be hollowed into vast halls without triggering catastrophic collapse, allowing the complex to survive more than 2,000 years despite monsoon rains, weathering, groundwater infiltration, and repeated geological stress. What immediately separates Ajanta from most ancient monuments is that nothing was assembled. Every column, ceiling, staircase, shrine, corridor, doorway, and sculpture was created by removing rock from a single cliff, rather than transporting building materials into place. Archaeologists estimate that tens of thousands of cubic meters of basalt were excavated throughout the construction of the complex. Unlike masonry architecture, where mistakes can often be corrected by replacing damaged blocks, every strike of the hammer permanently removed part of the mountain. A single error in determining roof thickness or cutting direction could have destroyed months or even years of work by causing fractures to spread through the remaining rock. Yet the largest prayer halls still retain roofs spanning nearly 15 meters in height and almost 30 meters in length, with remarkably little structural deformation. This achievement becomes even more difficult to explain when considering the geology of the Deccan Traps, one of the largest volcanic provinces on Earth. Formed by enormous basaltic eruptions around 66 million years ago, these lava flows cooled into successive layers, separated by joints, fractures, and weathered zones. Basalt appears visually solid, but its internal strength varies significantly depending on cooling history, mineral composition, and natural cracking. Modern engineers normally rely on drilling cores, seismic imaging, and laboratory testing before excavating large underground chambers within volcanic rock. The builders of Ajanta possessed none of these technologies, yet they consistently selected portions of the cliff capable of supporting immense cavities, while apparently avoiding the weakest geological zones. No surviving inscription explains how they identified stable rock before excavation began. As researchers reconstructed the carving sequence, another mystery gradually emerged. Physical evidence preserved on unfinished surfaces indicates that excavation generally progressed from the top downward rather than from the entrance inward. Workers first established the roof, then gradually descended through the interior until columns, walls, and floors finally emerged from the remaining stone. Such a method required every important structural decision to be made before the surrounding material had even been removed. Builders had to predict the final dimensions of chambers while standing inside solid rock, leaving virtually no possibility of correcting errors once excavation advanced. Even today, underground engineering projects depend heavily on continuous monitoring, because the removal of rock constantly redistributes stress throughout the surrounding mass. Ajanta's creators somehow managed this process across multiple generations without written engineering manuals that have survived. The stone columns themselves deepen the puzzle. Visitors naturally admire their elaborate capitals, carved figures, and decorative symmetry, yet structural engineers increasingly view them as integral load-bearing elements rather than purely artistic features. In several caves, the spacing between columns subtly changes instead of following perfectly uniform intervals. Some stand slightly closer together near wider roof spans, while others align with natural variations in the surrounding rock. These adjustments are often measured only in centimeters, but they influence how compressive forces travel through the remaining basalt. Whether these placements resulted from practical observation accumulated through experience or from a sophisticated understanding of rock mechanics remains impossible to determine, because the technical knowledge behind these decisions disappeared long ago while the stone itself continued carrying the load. Attention has also focused on the remarkable condition of the ceilings. Across more than 20 centuries, the caves have experienced countless monsoon seasons capable of delivering well over 2,000 millimeters of annual rainfall in parts of the region. Water is among the greatest enemies of rock-cut architecture because it penetrates fractures, dissolves weaker minerals, expands existing cracks through repeated wetting and drying cycles, and encourages vegetation whose roots exert tremendous mechanical pressure. Nevertheless, large sections of Ajanta remain structurally intact. Geological investigations have documented localized weathering and surface deterioration, but widespread roof failure never occurred. This unexpected durability suggests that ancient builders deliberately preserved sufficient roof thickness while exploiting the strongest portions of each basalt layer, although the precise criteria guiding those decisions remain unknown. Evidence surrounding the cave entrances suggests another overlooked engineering strategy. Rather than allowing seasonal runoff to flow directly across carved facades, many sections of the cliff incorporate carefully shaped channels and overhangs that redirect water away from vulnerable openings. Even subtle changes in rock geometry reduce the amount of water penetrating interior chambers. Modern conservation teams continue managing drainage because uncontrolled infiltration remains the greatest threat to the caves today. The fact that ancient excavators recognized this danger centuries before modern geology existed indicates that they possessed a sophisticated empirical understanding of long-term environmental processes, developed entirely through observation rather than formal scientific theory. The precision achieved across the interiors raises additional questions. Laser surveys have demonstrated that many ceilings, walls, and corridors remain strikingly regular despite having been carved entirely by hand. Long axial corridors maintain consistent alignment over considerable distances, while broad ceiling surfaces show only minimal deviation from their intended geometry. Such accuracy becomes especially remarkable considering that excavation occurred inside enclosed spaces illuminated only by oil lamps or reflected daylight entering from the facade. Every measurement had to be transferred manually, without electronic instruments, optical levels, or precision laser references. Even slight directional errors introduced early in excavation would have become increasingly magnified as work progressed deeper into the mountain. Yet the finished architecture displays a consistency difficult to reconcile with the technological limitations of the period. The famous Chaitya prayer halls introduce another phenomenon that continues attracting scientific interest. Their barrel-vaulted ceilings, apsidal plans, and carefully proportioned interior volumes generate unusually effective acoustics. Modern acoustic measurements have shown that chanting spreads evenly through these spaces, while limiting excessive echo that would otherwise reduce speech intelligibility. Curved ceilings reflect sound toward occupied areas, rather than dispersing it randomly, producing reverberation characteristics well-suited to ritual recitation. No ancient document attributes these properties to deliberate acoustic design, yet the geometry repeatedly achieves results that modern architects often model digitally before construction. Whether these effects emerged through centuries of experimentation or through intuitive refinement remains unresolved. Beyond the structural questions, Ajanta preserves one of humanity's most extraordinary collections of ancient mural painting. Created over several centuries, the paintings survive because artists first prepared the volcanic rock with multiple layers of clay, lime, organic fibers, and fine plaster before applying mineral pigments derived from natural sources such as red ochre, yellow ochre, carbon black, kaolin, and imported lapis-based blue in limited areas. Scientific analyses using microscopy, spectroscopy, and chemical characterization have shown that the painters carefully controlled both surface preparation and pigment composition to maximize durability. Even so, conservators still debate why certain sections retained exceptional color stability despite fluctuations in humidity, seasonal temperature changes, biological growth, and centuries of neglect after the caves were abandoned. Located in the Pindus Mountains of Thessaly, central Greece, Meteora appears to suspend entire stone monasteries atop towering sandstone pillars that rise as much as 600 meters above the surrounding valleys. More than 6 centuries after they were built, these massive structures continue to stand where geology, erosion, and repeated earthquakes suggest many of them should have gradually failed. Although local hermits had occupied the rock pinnacles for centuries, the first organized monastery at Meteora was established in the mid-14th century by Athanasios the Meteorite. Later travelers, Ottoman records, and modern archaeological surveys gradually documented the remarkable settlement, while geological studies revealed that the spectacular rock towers themselves formed approximately 25 to 30 million years ago from thick deposits of river gravels and sand that later became cemented into conglomerate rock before erosion sculpted the isolated pillars visible today. That geological history immediately raises an engineering mystery, because conglomerate is not an ideal construction material. Unlike granite or dense limestone, it consists of rounded pebbles and cobbles bound together by natural mineral cement, creating a rock mass whose internal strength can vary significantly from one location to another. Weathering gradually weakens exposed surfaces, water infiltrates natural fractures, and repeated thermal expansion slowly enlarges existing cracks. Modern engineers normally approach such formations cautiously because localized failures are difficult to predict. Yet medieval builders chose not only to occupy these pillars, but to place entire monasteries weighing hundreds of tons directly on their summits. The greatest unanswered question is not how the walls were erected, but why their attachment to the underlying rock has remained so remarkably stable for more than 600 years. Unlike castles founded on broad plateaus or deeply excavated bedrock, many Meteora monasteries appear to emerge directly from irregular rock surfaces with almost no visible transition between natural stone and masonry. Archaeological investigations show that builders carefully carved the summit itself into stepped platforms before laying foundations, allowing walls to follow the natural contours instead of forcing the rock into artificial geometry. This approach reduced concentrated stresses while maximizing contact between masonry and bedrock. Yet the exact methods used to anchor structural loads into highly variable conglomerate remain largely undocumented because virtually no medieval construction records describing the process have survived. The durability of those hidden connections becomes even more remarkable when viewed through the lens of structural geology. Conglomerate contains countless rounded stones embedded within finer sediments, meaning every foundation encounters changing mechanical properties over very short distances. Modern geotechnical engineering would normally require extensive mapping of fractures, discontinuities, and bearing capacity before placing heavy loads on such terrain. 14th century builders possessed none of these scientific tools, yet their choice of foundation locations appears extraordinarily selective. Many monasteries occupy the widest, most stable sections of individual pillars, while avoiding areas where major vertical joints or heavily weathered surfaces are now visible. Whether this resulted from generations of empirical observation or an exceptionally sophisticated understanding of rock behavior remains impossible to determine. Equally mysterious is the apparent absence of significant foundation displacement despite centuries of environmental stress. Greece ranks among Europe's most seismically active regions because the African plate continues moving beneath the Eurasian plate along the Hellenic arc. Historical records document numerous destructive earthquakes affecting Thessaly over the past several centuries, while instrumental observations confirm that moderate seismic activity remains frequent throughout central Greece. During every earthquake, the towering pillars naturally oscillate, transferring dynamic forces into every wall, arch, timber beam, and foundation stone. Yet structural surveys consistently show that most surviving monasteries have experienced remarkably limited large-scale foundation failure, compared with what engineers might expect from buildings of similar age constructed on fractured sedimentary rock. Their resilience becomes easier to appreciate when considering how medieval builders distributed weight across the landscape. Rather than concentrating enormous masses in isolated towers, they generally favored relatively low profiles, thick masonry walls, and timber roof systems capable of absorbing part of the seismic energy through controlled flexibility. Wooden beams hidden inside the structures acted as natural energy dissipators, reducing sudden stress concentrations during ground motion. Even so, these principles explain only part of the puzzle, because the hidden interface between masonry and conglomerate still performs the critical task of transferring thousands of tons of cumulative structural load into pillars continuously reshaped by erosion. That same erosion introduces another unanswered question. The rock towers of Meteora have stood exposed to rain, frost, wind, and seasonal temperature fluctuations for millions of years. Water slowly penetrates joints, dissolves mineral cement, and removes weaker sediments grain by grain. Gravity steadily enlarges fractures, eventually producing rockfalls that remain common throughout similar conglomerate landscapes. Nevertheless, the specific summits supporting the monasteries have retained sufficient integrity to preserve buildings that have remained occupied since the Byzantine period. Geologists attribute much of this longevity to unusually strong silica and calcite cement binding many portions of the conglomerate, but natural cementation alone cannot explain why the occupied summits appear disproportionately resistant compared with neighboring cliffs that have experienced repeated collapse. Construction itself presents another extraordinary logistical mystery. During the 14th and 15th centuries, there were no staircases connecting the valley floor with the monastery summits. Every block of stone, timber beam, roof tile, iron fitting, barrel of water, sack of grain, and bell had to be transported vertically using rope ladders, woven nets, and pulley systems suspended hundreds of meters above the ground. Historical descriptions mention these lifting devices, but provide almost no technical detail regarding anchoring systems, mechanical advantage, rope replacement schedules, or methods for stabilizing swinging loads in strong mountain winds. Considering that even a modest monastery required hundreds of tons of construction material, the absence of comprehensive engineering documentation remains one of Meteora's greatest historical gaps. Water management demonstrates another level of practical sophistication. Flat mountaintops exposed to seasonal rainfall can rapidly accumulate runoff capable of undermining foundations or accelerating rock weathering. Instead of allowing water to collect unpredictably, builders integrated stone gutters, drainage channels, underground cisterns, and carefully graded courtyards into the natural topography. Rainwater was directed away from vulnerable foundation zones while simultaneously being stored for daily use, reducing both erosion and dependence on external water supplies. Many of these hydraulic features continue functioning after several centuries with surprisingly limited modification, illustrating an environmental understanding far beyond what surviving written sources reveal. Rising above the Gardon River near Vers-Pont-du-Gard in southern France, Pont-du-Gard is far more than an ancient aqueduct. Nearly 2,000 years after Roman engineers completed it in the 1st century CE, this towering three-tier stone structure still stands where repeated floods, erosion, and the passage of time should have gradually destroyed it. Unlike many ancient monuments buried beneath sand or vegetation, Pont-du-Gard never completely disappeared from history. Medieval travelers continued to cross it, Renaissance scholars documented its remarkable proportions, and modern archaeological surveys, laser scanning, geological investigations, and structural engineering analyses have revealed how extraordinary the monument truly is. Built as part of the approximately 50-kilometer aqueduct supplying fresh water to the Roman city of Nemausus, now Nimes, the bridge itself rises almost 49 meters above the Gardon River, making it the tallest surviving Roman aqueduct bridge ever constructed. Its greatest mystery, however, begins beneath the water rather than above it. Few ancient bridges faced such an unpredictable river. The Gardon is famous throughout southern France for violent flash floods known locally as Gardonades. During major storms, water levels can rise by more than 7 meters within hours, while discharge increases dramatically, generating powerful currents capable of transporting entire trees and multi-ton boulders downstream. Modern bridges routinely require deep, reinforced foundations, scour protection systems, and continuous monitoring under similar hydraulic conditions. Pont-du-Gard had none of those technologies, yet its foundations have remained remarkably stable for nearly 20 centuries. Geological investigations indicate that the bridge was anchored directly onto exposed limestone bedrock, rather than deep artificial foundations. But that explanation solves only part of the puzzle. Bedrock alone cannot guarantee long-term stability when enormous hydraulic forces repeatedly attack the same structure. Floodwater scours sediment away from bridge piers, creating cavities that gradually weaken support. This process, known as scour, remains one of the leading causes of bridge failure worldwide, according to modern civil engineering research. Even today, engineers devote sophisticated computer models and underwater inspections to predicting scour around bridge foundations. No surviving Roman document explains how builders identified stable rock layers beneath an active river, how they prevented progressive erosion around each pier, or how they managed construction inside a flowing channel using 1st century technology. Laser measurements performed during recent conservation projects show that several primary piers remain astonishingly close to their original alignment, displaying only minimal deformation despite nearly 2,000 years of seasonal flooding. That structural stability becomes even more surprising when the bridge's immense weight is considered. Historians estimate that approximately 50,000 tons of locally quarried limestone were assembled without modern concrete or steel reinforcement. Individual blocks commonly weigh between 2 and 6 tons, while several exceed 10 tons. Unlike many later masonry bridges, Pont du Gard relies almost entirely on precisely fitted dry stone construction. Mortar plays only a limited role. Instead, the enormous compressive force generated by the bridge itself locks each block into position. Such a system functions only if every contact surface is cut with exceptional precision. A slight deviation repeated across hundreds of stones would gradually redistribute loads, increasing tensile stresses that stone cannot resist. Yet the monument continues carrying its own weight almost exactly as intended by Roman engineers. The bridge's elegant appearance also conceals an unusually sophisticated structural strategy. Rather than repeating identical arches across all 3 levels, Roman builders gradually reduced the span size toward the top. The lowest level contains only 6 massive arches spanning the river. Above them stand 11 smaller arches, while the highest level supporting the water channel consists of 35 narrow arches. This arrangement significantly decreases the dead load imposed on the lower structure, while distributing compressive forces more evenly through the piers. Modern finite element simulations performed by structural engineers have demonstrated that stress concentrations remain surprisingly low throughout much of the bridge, suggesting an intuitive understanding of load paths that would not be formally described until many centuries later. No mathematical design calculations survive, leaving researchers uncertain whether Roman builders relied entirely on accumulated experience or possessed engineering methods now lost. As impressive as the stonework appears, the aqueduct hidden along the upper level introduces another layer of mystery. Pont du Gard formed only one section of an entire hydraulic system extending roughly 50 kilometers from springs near Uzès to Nîmes. Across that entire distance, the water descended only about 17 meters, producing an average gradient of approximately 34 centimeters per kilometer, or just 0.034%. Such an extraordinarily gentle slope required remarkable surveying accuracy. If the gradient became too steep, water velocity would increase, accelerating erosion inside the channel. If the slope flattened too much, sediment would accumulate until the aqueduct eventually became blocked. Roman surveyors possessed instruments such as the chorobates and groma, yet historians continue debating whether these devices alone could consistently achieve the precision required across such a long route. Even slight cumulative errors measured in centimeters could have rendered the entire system ineffective. Construction methods raise equally difficult questions. The highest stones were placed nearly 50 meters above the river, requiring the lifting and positioning of blocks weighing several tons with no steam engines, hydraulic cranes, or steel cables. Archaeologists believe Roman treadwheel cranes probably played an important role because similar lifting machines are documented elsewhere in the empire. Nevertheless, no direct archaeological evidence survives showing exactly how such equipment operated at Pont du Gard. Massive wooden scaffolding, temporary earthen ramps, complex pulley systems, or combinations of all 3 have been proposed, yet none can currently be demonstrated with certainty. Time has removed almost every trace of the temporary engineering that made permanent construction possible. The bridge's remarkable survival owes much to its interaction with the river itself. Each pier incorporates sharply pointed upstream cutwaters that divide approaching currents before they strike the structure. Instead of presenting broad, flat surfaces to floodwater, the bridge encourages flow separation, reducing hydraulic pressure while limiting vortex formation around the foundations. The wide spacing between the lower arches further allows enormous flood volumes to pass through rather than pushing directly against a continuous barrier. These principles remain fundamental in modern bridge engineering. But whether Roman designers understood the underlying fluid mechanics or simply refined centuries of practical observation remains impossible to determine. What is certain is that many younger masonry bridges lacking these features suffered catastrophic collapse, while Pont du Gard endured. Centuries of exposure have only deepened the mystery. Floods, temperature changes, and weathering should have weakened the structure, yet most original stonework remains remarkably intact. Although some repairs were made, especially after its use as a road bridge, the Roman core still functions as intended. Modern engineering can explain parts of its durability, but not how Roman builders achieved such precise surveying, stable foundations, and coordinated construction under such challenging conditions. Masada rises above the Dead Sea in southeastern Israel, crowning an isolated rock plateau where an entire fortress has remained standing for more than 2,000 years, despite occupying cliffs that engineering suggests should have become progressively unstable long ago. Although the dramatic Roman siege made Masada famous for centuries, its true architectural complexity only became clear after systematic excavations led by Yigael Yadin between 1963 and 1965. Followed by decades of geological mapping, structural surveys, aerial photography, laser scanning, and conservation studies that revealed one of the most sophisticated mountain fortresses ever built during the reign of Herod the Great, between approximately 37 and 31 BCE. The greatest mystery is not the fortress itself, but the ground beneath it. Masada occupies the summit of an isolated mesa overlooking the Dead Sea, rising roughly 450 meters above the surrounding landscape, while the plateau extends for nearly 600 meters in length and about 300 meters in width. Much of the northern palace and several defensive walls stand astonishingly close to sheer cliffs where gravity, erosion, and repeated seismic activity should have gradually weakened the underlying rock. Geological surveys show that the mesa consists primarily of dolomite and limestone, resting above softer marl layers, formations that commonly develop fractures as weathering progresses. Yet after more than 20 centuries, much of the original foundation remains remarkably stable. Modern engineers can explain why the plateau is relatively resistant, but they still cannot fully reconstruct how Herod's builders determined which cliff edges could safely support thousands of tons of masonry without triggering large-scale slope failure. No surviving Roman or Judean documents describe the surveying methods, foundation preparation, or rock testing that must have preceded construction on terrain that even today would require detailed geotechnical analysis. That unanswered question becomes even more remarkable when the northern palace is examined in detail. Rather than placing a royal residence safely in the center of the plateau, Herod ordered an elaborate three-level palace to be constructed directly against the northern cliff. 3 terraces descend the rock face one beneath another, connected by stairways carved into the mountain itself. The lowest levels project toward open space, with massive retaining walls supporting elegant halls and semicircular balconies overlooking the Dead Sea. The builders achieved this without reinforced concrete, steel anchors, or deep-drilled foundations. Instead, carefully shaped limestone blocks, lime mortar, retaining walls, and precisely distributed loads appear to have transferred enormous weight into selected portions of the cliff. Although restoration has stabilized damaged sections, the surviving original masonry demonstrates an understanding of load distribution that continues to impress structural engineers. Exactly how ancient surveyors calculated these safe-bearing zones remains uncertain, because none of the construction records have survived. The surrounding landscape makes that achievement even more difficult to explain. Masada lies within the influence of the Dead Sea Transform, one of the Middle East's major active fault systems extending for more than 1,000 kilometers. Historical sources and geological evidence indicate that destructive earthquakes struck the region in 31 BCE, 363 CE, 749 CE, and during several later events capable of damaging settlements throughout the Jordan Rift Valley. Despite repeated seismic shaking over 2 millennia, substantial sections of Masada's fortifications remain standing. Archaeological investigations suggest that many defensive walls were constructed using a casemate design consisting of 2 parallel stone walls filled with smaller stones, earth, and interior chambers. Modern structural analysis indicates that this arrangement distributes stress more effectively than a single solid wall, while reducing overall weight, allowing limited movement during seismic events without catastrophic collapse. Whether Herod's engineers intentionally designed these walls for earthquake resistance cannot be proven, but their long-term survival demonstrates a remarkable practical understanding of structural behavior. Even if the buildings could survive earthquakes, another engineering challenge seems almost impossible. Masada occupies one of the driest regions in the Levant, where annual rainfall averages only around 50 millimeters, almost all arriving during short winter storms. Permanent springs do not exist on the summit, yet the fortress supported hundreds of residents and could shelter far larger populations during military emergencies. To solve this problem, Herod's engineers created one of the most advanced ancient water systems ever constructed in a desert environment. Channels cut into surrounding slopes intercepted seasonal flash floods flowing through nearby wadis before directing the water into a chain of enormous cisterns carved into the mountainside below the fortress. Archaeological estimates suggest the complete storage system held approximately 40,000 to 50,000 cubic meters of water, enough to sustain a prolonged occupation. The entire network functioned entirely through gravity, requiring no pumps or mechanical lifting devices. The precise gradients of the channels remain remarkably accurate despite the rugged terrain, demonstrating careful hydraulic planning that continues to attract engineering study. Equally impressive is the durability of the reservoirs themselves. Water storage structures exposed to intense desert heat, dissolved salts, and repeated wetting and drying normally deteriorate rapidly. Yet many of Masada's cisterns preserve their original waterproof lining. Laboratory analysis has identified sophisticated lime plaster, incorporating carefully graded aggregates and crushed ceramic fragments that improved both strength and water resistance. Similar hydraulic plasters are known elsewhere in the ancient Mediterranean, but the exact production methods, firing temperatures, and mixing proportions that produced such long-lasting performance remain only partially understood because ancient technical manuals describing the process have not survived. As the investigation expands across the plateau, evidence repeatedly suggests that nearly every major structure was carefully adapted to the natural topography rather than forcing the mountain into an artificial shape. Drainage channels guided intense seasonal rainfall away from foundations before destructive erosion could develop. Retaining walls stabilized vulnerable slopes, and terraces followed the strongest portions of the underlying bedrock. These solutions appear deceptively simple, yet together, they created a fortress capable of enduring conditions that routinely destroy exposed mountain architecture. Modern geological surveys continue to identify erosion scars surrounding the mesa, while the principal occupation areas remain comparatively stable, suggesting the builders possessed an exceptionally accurate practical understanding of local geology without the benefit of modern instruments. The logistics behind the project remain another unresolved puzzle. During Herod's reign, enormous quantities of dressed limestone, timber, plaster, decorative stone, food supplies, and construction equipment had to reach the isolated summit in an environment where summer temperatures frequently exceed 40 degrees Celsius. Archaeologists have identified ancient access routes and construction phases, but no surviving documents explain how thousands of tons of material were transported, organized, and assembled with such precision on an elevated plateau surrounded by steep cliffs. Every completed wall, therefore, represents not only architectural skill, but also an extraordinary level of planning that has largely disappeared from the historical record. Karnak stands on the east bank of the Nile at Luxor in southern Egypt, where one of the largest religious complexes ever built has remained standing for more than 3,000 years. The greatest mystery is not who constructed it, but why a forest of colossal stone columns still supports itself on soft river sediments in a landscape repeatedly shaped by floods, groundwater, earthquakes, and time. Unlike many ancient cities that disappeared beneath sand, Karnak was never truly lost. Greek and Roman travelers described its enormous temples. 19th century expeditions began systematic documentation, and modern archaeological excavations combined with laser scanning, ground-penetrating radar, geological surveys, and structural engineering have gradually revealed the immense scale of the complex. Covering more than 100 hectares and expanded continuously for nearly 2,000 years by around 30 pharaohs, Karnak represents one of humanity's longest-running construction projects, yet many of its most remarkable engineering achievements remain only partially understood. The greatest puzzle lies inside the Great Hypostyle Hall, where 134 sandstone columns continue to stand after more than 3,300 years. Arranged across an area of approximately 5,000 square meters, the central columns rise to nearly 24 meters, while the largest measure roughly 3.5 meters in diameter. Individual columns are estimated to weigh between 70 and 120 metric tons, and together they once supported an enormous stone roof composed of equally massive architraves. Modern engineers understand how compression works in principle, but the remarkable stability of this immense stone forest raises questions that remain difficult to answer. Every column transfers tremendous vertical loads into the ground with extraordinary consistency despite thousands of years of environmental change. Even slight differences in settlement should have produced visible tilting, progressive cracking, or cascading structural failures, yet the majority of the columns remain remarkably upright. Their survival suggests that ancient builders possessed an exceptionally sophisticated understanding of load distribution, foundation preparation, and structural balance long before formal engineering science existed. That mystery becomes even more remarkable when the underlying geology is considered. Karnak stands only a short distance from the Nile, where thick layers of alluvial sediments accumulated over thousands of years through seasonal flooding. Such soils generally compress under heavy loads, especially when groundwater levels fluctuate over long periods. Modern construction on similar terrain frequently requires reinforced foundations, deep piles, or complex ground improvement techniques to prevent uneven settlement. The builders of Karnak had none of these technologies, yet the enormous weight of the hypostyle hall has remained astonishingly stable. Geological investigations suggest that the Egyptians may have excavated through weaker sediments until reaching more compact layers before carefully preparing stone foundation beds capable of spreading the enormous loads. Ground-penetrating radar has identified buried structural elements beneath portions of the temple, while archaeological excavations reveal carefully laid foundation courses, but no surviving construction records explain exactly how the ground was engineered to support tens of thousands of tons of sandstone for over 3 millennia. Much of the original construction process therefore remains hidden beneath the monument itself. As the scale of the project becomes clearer, another unresolved challenge immediately appears. Constructing the foundations was only the beginning, because every massive column first had to be raised into position with extraordinary precision. Many of these monolithic sandstone drums were transported from quarries hundreds of kilometers upstream before being assembled into towering columns exceeding the height of a modern 7-story building. No cranes, steel cables, hydraulic systems, or powered lifting machinery existed during the New Kingdom. Archaeologists generally favor combinations of earthen ramps, wooden sledges, ropes, and levers, yet no complete archaeological evidence has ever demonstrated exactly how columns approaching 100 tons were erected vertically without catastrophic failure. Every drum had to remain perfectly aligned, because even small positioning errors would accumulate throughout the structure, threatening the stability of the roof above. Despite more than a century of experimental archaeology, the complete lifting sequence remains one of ancient Egypt's most enduring engineering questions. The challenge continued even after every column stood in place, because the builders then elevated gigantic sandstone architraves onto the capitals nearly 20 meters above the ground. Individual roof beams commonly measured between 8 and 10 meters in length and weighed roughly 40 to 70 tons. Installing blocks of this size demanded precise control throughout every stage of lifting and placement. If a beam shifted unexpectedly during installation, it could fracture the supporting columns beneath it or trigger progressive collapse across adjacent sections. Yet many of these immense stones were positioned with astonishing accuracy, distributing their weight almost evenly across the column capitals. Although researchers have proposed increasingly sophisticated ramp systems surrounding completed columns, no universally accepted reconstruction has demonstrated exactly how these roof stones reached their final positions. The structural precision visible today therefore exceeds what surviving evidence can fully explain. The remarkable stability of Karnak extends far beyond its famous columns. Rising above the complex stands the unfinished silence of another engineering achievement that continues to puzzle specialists: the granite obelisk of Hatshepsut. Reaching approximately 29.5 meters in height and weighing an estimated 320 to 350 metric tons, it remains among the tallest surviving obelisks ever erected in Egypt. Unlike modern towers secured by steel reinforcement or deep anchoring systems, the obelisk depends almost entirely upon its own carefully balanced weight, resting on an accurately prepared stone base. Maintaining vertical stability for roughly 3,500 years requires extraordinarily precise control of its center of gravity, because even slight foundation movement could have introduced dangerous tilting forces. Engineers can calculate why it stands today, yet exactly how ancient surveyors achieved the necessary positioning accuracy using only simple measuring instruments continues to inspire debate. Equally impressive is the precision with which thousands of sandstone blocks were fitted throughout the temple. Luxor experiences extreme seasonal heat, with summer temperatures frequently exceeding 45 degrees Celsius, while significantly cooler nights create continuous cycles of thermal expansion and contraction. Across more than 3 millennia, these repeated temperature fluctuations have subjected the masonry to well over 1 million expansion cycles. In many stone structures, such relentless movement gradually opens joints, weakens contacts, and accelerates cracking. At Karnak, however, numerous joints remain remarkably tight despite centuries of environmental stress. Researchers believe careful selection of stone, thoughtful orientation of bedding planes, exceptionally flat contact surfaces, and highly accurate stone dressing all contributed to this resilience. Although the exact construction tolerances achieved by ancient masons cannot be reconstructed with certainty because the tools, workshops, and technical manuals that once guided the work have almost entirely disappeared. The entire complex also reflects a level of surveying precision that extends beyond structural engineering. The principal axis of the Temple of Ammon aligns closely with significant solar events associated with religious ceremonies. Yet the temple was not built in a single campaign. Successive rulers expanded, modified, and rebuilt sections over nearly 2,000 years, while largely preserving the original geometric organization. Maintaining such long-term alignment required repeated measurements across an increasingly crowded architectural landscape, without optical instruments, electronic positioning systems, or magnetic compasses. Archaeologists understand many of the astronomical principles available to Egyptian surveyors, but reconstructing the exact field methods that preserved this remarkable consistency across dozens of generations remains far more difficult. Even the surviving inscriptions deepen the mystery. Thousands of hieroglyphs and carvings remain visible despite centuries of harsh weather. Many retain sharp details, likely due to high-quality Nubian sandstone and careful carving techniques. Yet their exceptional preservation suggests ancient craftsmen had a deep understanding of stone, gained through long experience. Rising nearly 200 meters above the tropical forests of central Sri Lanka, Sigiriya appears to balance an entire royal city on top of a single block of ancient rock. More than 15 centuries after its construction, the greatest mystery is not who built it, but why a palace of such immense weight still stands on a summit that geology suggests should have been far more vulnerable to weathering, erosion, and structural failure. Unlike many lost ancient cities, Sigiriya was never completely forgotten. Medieval Buddhist monks continued to occupy parts of the surrounding area after the royal capital was abandoned, while European attention returned in the early 19th century through descriptions by British officials and explorers. Systematic archaeological excavations during the 20th century gradually revealed that the site was not simply a fortress, but an extraordinarily sophisticated combination of palace, hydraulic landscape, defensive complex, and engineered mountain settlement, dating primarily to the reign of King Kashyapa I between AD 477 and 495. The mystery begins with the rock itself. Sigiriya is the hardened volcanic plug of an extinct magma chamber. Left standing after millions of years of erosion removed the softer rock surrounding it. Today, the isolated monolith rises approximately 180 to 200 meters above the surrounding plain, with steep granite walls that offer remarkably little natural space for large-scale construction. Yet ancient engineers transformed this narrow summit into an elaborate palace complex containing royal buildings, pools, reservoirs, terraces, gardens, and defensive walls. The greatest unanswered engineering question is how thousands of tons of masonry remained stable on a summit with no conventional foundation beneath it. Unlike buildings constructed on prepared ground, every structure at Sigiriya depended entirely upon the natural geometry of the rock. Geological surveys have identified numerous fractures running through the granite, the inevitable result of millions of years of cooling and weathering. Modern engineers normally avoid concentrating heavy loads near fractured rock edges because differential movement can eventually produce instability. Yet the surviving palace foundations reveal that builders carefully distributed major structures across the summit, instead of clustering them at its margins. Archaeologists believe extensive portions of the uneven granite surface were cut and leveled before construction began, producing stable platforms that transferred weight directly into the strongest parts of the monolith. Exactly how ancient builders evaluated the mechanical stability of individual sections of exposed granite without modern geological instruments remains unknown. The longer researchers examine Sigiriya, the more remarkable its water management becomes. Central Sri Lanka receives roughly 2,000 to 2,500 millimeters of rainfall each year, enough to destroy poorly designed mountain settlements through erosion, landslides, and continuous water infiltration. Rain falling onto the summit could easily have accumulated inside natural depressions, gradually widening cracks through repeated wetting, chemical weathering, and plant growth. Instead, careful topographic surveys have shown that much of the summit was shaped with subtle gradients, directing runoff into narrow drainage channels carved directly into the rock. Water rarely remained trapped for long periods, reducing hydraulic pressure while minimizing long-term structural deterioration. Many of these drainage pathways continue functioning after more than 1,500 years, despite continuous exposure to tropical rainfall. That sophisticated understanding of water extended far beyond simple drainage. At the foot of Sigiriya lies one of the most advanced hydraulic landscapes of the ancient world, incorporating reservoirs, canals, pools, underground conduits, and geometrically planned water gardens covering several hectares. Excavations have demonstrated that the entire system operated primarily through gravity rather than mechanical pumping. Water flowed between reservoirs using carefully controlled elevation differences, while pressure generated naturally within underground channels supplied ornamental fountains. During periods of heavy rainfall, several of these fountains can still function today, making Sigiriya one of the very few ancient hydraulic systems whose original engineering principles remain visibly operational. Maintaining sufficient hydraulic pressure across such a complex landscape required construction tolerances measured in extremely small changes of elevation, yet no written engineering documents survive to explain how those gradients were established with such precision. The steep slopes below the summit present another technical puzzle. Large retaining walls, terraces, stairways, and artificial platforms were constructed across terrain that would normally be vulnerable to gradual downslope movement under centuries of seasonal rainfall. Modern slope stabilization often relies on reinforced concrete, deep anchors, or steel supports, none of which existed during the 5th century. Instead, Sigiriya's builders appear to have exploited the natural structure of the granite itself, placing retaining walls where underlying rock provided maximum resistance, while minimizing unnecessary loading near unstable edges. Many of these retaining structures remain remarkably well aligned despite repeated cycles of tropical weathering that have continued for over 15 centuries. Their survival suggests an advanced, practical understanding of rock mechanics that archaeology has yet to fully reconstruct. Few features illustrate that sophistication more vividly than the famous mirror wall. Built along a narrow ledge beneath the western face of the rock, this polished plaster surface once reflected the image of visitors, clearly enough for medieval writers to compare it to an actual mirror. Scientific analysis has identified multiple layers of fine lime plaster mixed with carefully selected mineral components and organic additives before being polished to an exceptionally smooth finish. Although centuries of exposure have reduced its original brilliance, sections still preserve an unusual reflective quality. Researchers continue investigating the precise composition and polishing techniques because no surviving historical record explains how such a durable finish was achieved under tropical environmental conditions. Above the mirror wall, another engineering achievement continues to challenge conservation scientists. The celebrated Sigiriya frescoes were painted directly onto sheltered sections of the vertical granite cliff, using mineral pigments applied over specially prepared plaster. More than 1,500 years of humidity, seasonal rainfall, biological growth, and temperature fluctuations have damaged portions of the paintings. Yet dozens of figures retain remarkable color intensity. Laboratory studies indicate the use of finely prepared lime plaster combined with stable mineral pigments capable of resisting long-term chemical degradation. Even so, the complete production process remains only partially understood, leaving unanswered questions about why these paintings survived far longer than many other ancient murals exposed to similar climates. Perhaps the most practical mystery concerns logistics rather than construction. Every stone block, timber beam, ceramic pipe, brick, roofing material, food supply, and container of water required for building the summit palace had to be transported nearly 200 vertical meters above the surrounding plain. Archaeologists estimate that thousands of tons of construction material were ultimately placed on the summit, yet no direct archaeological evidence has revealed the lifting systems responsible. Temporary earthen ramps, timber scaffolding, rope hauling systems, and inclined access roads have all been proposed, but none can presently account for every stage of construction with complete confidence. Unlike many ancient monuments where unfinished elements reveal building techniques, Sigiriya preserves remarkably few clues regarding the engineering methods used to raise its enormous construction materials. Few monuments challenge modern engineering more convincingly than the Aqueduct of Segovia in central Spain. Nearly 2,000 years after Roman engineers raised its towering arches above the city, the structure still carries its own enormous weight, almost exactly as intended, even though it was built without mortar, steel, or any chemical binding material between its stones. Unlike many ancient monuments that disappeared beneath soil or collapsed into ruins before being rediscovered, the Aqueduct of Segovia remained visible throughout history. Roman records, medieval chronicles, Renaissance drawings, archaeological excavations, laser scanning, photogrammetry, geological investigations, and structural engineering studies have gradually revealed how extraordinary the monument truly is. Constructed during the late 1st or early 2nd century CE, most likely under the reigns of Emperors Domitian, Nerva, or Trajan, the aqueduct originally transported fresh water for approximately 17 kilometers from the Frio River to the Roman city of Segovia. Its most famous section stretches roughly 813 meters across the city, reaches almost 28.5 meters in height, contains 167 arches supported by 120 pillars, and consists of more than 20,000 granite blocks, weighing many thousands of tons collectively. Yet the measurements alone fail to explain why the monument still exists. The greatest mystery begins with a fact that appears almost impossible even by modern standards. Every visible granite block was placed without mortar. There is no cement locking the stones together, no iron reinforcement hidden inside the pillars, and no metal clamps tying neighboring blocks into a rigid frame. Instead, every component survives because gravity continuously compresses the stones against one another. This principle sounds deceptively simple, but structural mechanics show that dry masonry remains stable only while the internal line of thrust stays entirely within each arch. If even one critical section shifts beyond that narrow zone, tensile forces develop where stone possesses almost no strength, allowing cracks to spread rapidly until the entire arch collapses. The remarkable reality is that this never occurred despite almost 2 millennia of environmental change. Understanding why requires examining the extraordinary precision of Roman construction. Granite typically measures between 6 and 7 on the Mohs hardness scale, making it significantly harder to shape than limestone or sandstone. Every block, therefore, required repeated cutting, dressing, lifting, transporting, and final positioning before another stone could be added above it. Archaeological surveys reveal that although individual stones vary slightly in dimension, their contact surfaces were finished accurately enough to distribute compressive forces evenly across thousands of interfaces. Modern laser scans demonstrate that neighboring blocks frequently meet with extremely small gaps despite centuries of weathering. Reproducing such consistency across more than 20,000 separate stones without powered machinery represents one of the greatest unresolved achievements of Roman stoneworking. Historians know Roman builders employed iron tools, wooden cranes, lifting treadwheels, templates, measuring rods, plumb lines, and leveling instruments such as the chorobates. Yet no surviving technical document explains how quality control remained sufficiently accurate over an entire project of this scale. That mystery becomes even greater once the arches themselves are considered. A single Roman arch can tolerate remarkable compression, but Segovia contains 167 connected arches that continuously transfer loads from one opening to the next before finally reaching the foundations. Structural simulations performed during recent conservation projects indicate that the stability of every arch depends upon the stability of neighboring arches, meaning small movements can propagate throughout the entire system. Under ordinary circumstances, differential settlement beneath only one supporting pier should gradually distort load paths, eventually producing fractures in multiple adjacent arches. Instead, measurements collected over decades reveal that most of the monument remains extraordinarily well aligned. This suggests that Roman engineers understood the relationship between geometry, load distribution, and foundation behavior with a sophistication that written historical sources never fully describe. The foundations themselves introduce another engineering puzzle. The visible arches represent only part of the structure, because enormous loads descend into the ground beneath every pillar. Together, the granite masonry weighs tens of thousands of tons, creating immense pressure on the underlying soil. Any uneven settlement accumulated over centuries should have altered the geometry of the arches enough to threaten collapse. Geological investigations indicate that Roman builders carefully selected competent ground and adapted foundation dimensions according to local conditions, yet exactly how they evaluated bearing capacity without modern geotechnical testing remains uncertain. No surviving manual explains how engineers estimated soil strength, identified weak layers, or determined the depth required to achieve long-term stability. Nevertheless, the monument demonstrates that their practical methods proved remarkably successful. As researchers continued examining the aqueduct, another unexpected advantage emerged from what originally appeared to be a primitive construction technique. Because the granite blocks are not rigidly bonded by mortar, they can respond to microscopic movements caused by thermal expansion and contraction. Granite expands during hot summer afternoons and contracts again during cold nights, repeating this cycle millions of times over 2,000 years. A completely rigid structure would accumulate internal stress that eventually produces fractures. But Segovia behaves differently. Tiny adjustments between neighboring stones help dissipate stress before dangerous concentrations develop, allowing the entire monument to accommodate seasonal movement while preserving its overall geometry. Some structural engineers have compared this behavior to a passive expansion system, although it emerged centuries before modern engineering formulated the underlying principles. Water transport presented an equally demanding challenge. Gravity alone powered the entire aqueduct across approximately 17 kilometers, meaning its channel required an exceptionally consistent gradient from source to destination. If the slope became too steep, water velocity would increase enough to erode the channel and damage the structure. If it became too shallow, sediment would accumulate and eventually obstruct the flow. Roman surveyors therefore had to maintain an almost continuous elevation change across valleys, ridges, and uneven terrain, without satellites, electronic instruments, or laser equipment. Ancient authors, including Vitruvius, described surveying devices such as the chorobates for establishing level lines, but historians still debate the practical accuracy these instruments achieved over such distances. The surviving aqueduct suggests Roman surveying techniques reached a level of precision that continues to impress modern civil engineers. Natural disasters should also have shortened the monument's lifespan long ago. Central Spain experiences repeated freeze-thaw cycles, seasonal temperature extremes, heavy rainfall, and occasional seismic activity. Each process gradually weakens exposed stone by opening microscopic fractures, allowing water penetration and accelerating weathering. Conventional expectations would predict progressive deterioration, eventually leading to structural failure. Instead, conservation surveys consistently report that most original Roman masonry remains intact. Although restoration campaigns repaired localized damage caused by human activity and isolated deterioration, the primary structural framework continues to rely overwhelmingly on original granite blocks placed nearly 2 millennia ago. This exceptional survival indicates that the monument possessed a much greater safety margin than its appearance initially suggests. Even the proportions of the upper arcade contribute to the mystery. Rather than relying upon massive solid walls, Roman engineers chose 2 stacked levels of arches that significantly reduced overall weight, while maintaining sufficient stiffness to resist compression. The design simultaneously minimized material consumption and controlled the distribution of forces throughout the structure. Modern finite element analyses demonstrate that this arrangement efficiently channels loads downward through the piers, while limiting excessive stress concentrations. Although engineers today can mathematically explain why the system works, the methods Roman builders used to determine those proportions remain largely unknown because no detailed construction calculations survive. In the deserts of northwestern Saudi Arabia, Hegra rises from isolated sandstone outcrops like a city carved by impossible precision. Nearly 2,000 years after its creation, its towering facades still stand, where geology suggests they should have slowly disappeared. The site remained largely unknown to the outside world for centuries after the decline of the Nabatean kingdom, until European explorers, most notably Charles Montagu Doughty during the 19th century, documented the monumental tombs in detail. Modern archaeological excavations, satellite mapping, laser scanning, and geological surveys have since revealed that Hegra, known historically as Madain Salih, was the Nabateans' southernmost major city. UNESCO recognizes the site as containing 111 monumental rock-cut tombs, 94 of which display elaborately carved facades dating primarily between the 1st century BCE and the 1st century CE. Yet the more researchers measure these monuments, the more one central engineering mystery dominates every discussion. The greatest puzzle is not how the facades were decorated, but why they still exist at all. Unlike temples carved into exceptionally hard granite, Hegra was sculpted directly into sandstone, a sedimentary rock that is significantly more vulnerable to erosion. The region experiences some of the harshest environmental conditions on the Arabian Peninsula. Summer temperatures frequently exceed 45 degrees Celsius before dropping sharply after sunset, creating continuous cycles of thermal expansion and contraction inside the rock. Seasonal winds transport enormous quantities of quartz sand that gradually abrade exposed surfaces, while rare but intense desert storms produce flash floods capable of forcing water deep into microscopic fractures. Modern geomorphology predicts that sharp edges, projecting cornices, and slender decorative columns should progressively round off or fracture under these combined processes. Instead, many of Hegra's monumental facades preserve crisp architectural lines, intact capitals, finely cut moldings, and symmetrical stair-like crow steps that remain recognizable after almost 2 millennia. Geological studies suggest that the Nabateans deliberately selected sandstone blocks, cemented by stronger silica and carbonate minerals, while avoiding heavily fractured outcrops. But no surviving records explain how builders identified internal rock quality without drilling, excavation, or modern geological instruments. Even today, engineers often rely on laboratory testing before cutting structural stone, yet ancient builders appear to have made remarkably accurate decisions simply by observing the landscape. That mystery becomes even deeper once the construction process is reconstructed. Archaeological evidence demonstrates that Nabatean craftsmen usually began carving from the top of each rock formation before gradually working downward toward the entrance. This sequence reduced the risk of falling debris damaging completed decoration below and allowed gravity to remove waste material naturally. However, it also demanded extraordinary planning, because every measurement established near the summit determined the alignment of everything beneath it. A deviation of only a few centimeters at the highest point would become dramatically amplified over facades reaching 15 to more than 20 meters in height. Laser surveys performed during recent conservation projects reveal surprisingly consistent symmetry across many monuments, indicating that builders maintained remarkable geometric control throughout the entire carving process. No construction drawings have survived, no measuring instruments have been recovered that explain such precision, and very little evidence of major corrective carving appears on the finished facades. The practical surveying methods behind this accuracy remain uncertain. The structural challenge continued inside the mountain itself. Each completed tomb required workers to remove enormous quantities of sandstone while preserving a stable shell capable of supporting the mass above. Instead of assembling walls block by block, the Nabateans hollowed chambers directly into living rock, transforming solid hills into carefully balanced structures. Every strike removed material that originally contributed to the mountain's internal stress distribution. Removed too much from the wrong location, and fractures could propagate toward the ceiling, eventually causing catastrophic collapse. Modern rock mechanics demonstrates how excavation redistributes compressive and tensile stresses throughout surrounding stone, making unsupported cavities especially vulnerable if natural bedding planes or hidden joints are encountered. Nevertheless, the majority of Hegra's chambers have remained structurally stable for nearly 2,000 years, despite countless seasonal expansion cycles and natural weathering. Researchers increasingly suspect that Nabatean builders possessed an exceptional empirical understanding of rock behavior developed through generations of quarrying and excavation, although the knowledge itself disappeared long before it could be recorded. As the monuments continue to survive, another question gradually emerged from the desert climate itself. Although rainfall is scarce, northwestern Arabia occasionally experiences violent cloudbursts capable of generating destructive flash floods. Water-penetrating sandstone often dissolves mineral cement, transports salt into microscopic pores, and eventually causes granular disintegration when crystals expand during evaporation. Conservation scientists identify salt weathering as one of the greatest long-term threats to sandstone monuments worldwide. Yet numerous tombs at Hegra show evidence that runoff was intentionally managed. Slight overhanging cornices, carefully positioned entrances, subtly inclined surfaces, and narrow drainage channels appear to redirect water away from the most delicate carvings. These features are almost invisible to casual visitors, but significantly reduce the amount of flowing water reaching vulnerable architectural details. Whether these drainage solutions resulted entirely from accumulated experience or from a more systematic understanding of erosion remains unresolved, but their effectiveness is demonstrated by the survival of intricate decorative elements that should have been among the first casualties of desert weathering. The choice of where to build may have been equally sophisticated. Rather than carving every available cliff, Nabatean engineers repeatedly selected isolated sandstone monoliths separated across the landscape. Geological mapping shows that neighboring rock formations often possess very different fracture densities, grain sizes, and cementation histories despite standing only a short distance apart. One outcrop may remain mechanically stable, while another develops extensive cracking under identical environmental conditions. The distribution of Hegra's tombs suggests deliberate avoidance of weaker formations, implying that builders evaluated structural integrity before carving began. How they distinguished reliable rock from unstable stone without modern geological analysis remains one of the site's least understood technical achievements. The monuments have also endured a region influenced by active tectonics associated with the Red Sea Rift. Northwestern Arabia has experienced numerous earthquakes throughout historical time, producing repeated ground vibrations capable of exploiting existing weaknesses in stone. Unlike masonry buildings constructed from individual blocks connected by mortar, Hegra's tombs remain integral parts of the mountains from which they were carved. This monolithic design eliminates joints that often become failure points during seismic movement, allowing stress to disperse more uniformly through continuous rock. Even so, the survival of slender carved pilasters, projecting cornices, and delicate decorative features after centuries of seismic activity continues to surprise structural specialists who model the long-term response of weathered sandstone. Hegra preserves almost no written record of the engineering behind its construction. While inscriptions note owners and dates, they reveal nothing about methods or techniques, leaving the monuments as silent evidence of a lost engineering tradition. Perched in the volcanic highlands of northern Ethiopia, Lalibela appears to hide an entire sacred city beneath the surface. Nearly 8 centuries after its creation, 11 churches carved directly into solid rock continue to stand, where engineering suggests many of them should have gradually failed. Unlike many famous archaeological sites that disappeared beneath sand or vegetation, Lalibela was never truly lost. European accounts reached the outside world during the early 16th century through the writings of Portuguese priest Francisco Alvarez, while systematic archaeological documentation expanded during the 19th and 20th centuries. Modern geological surveys, laser scanning, and structural studies have since revealed that these monuments were never assembled from blocks of stone. Instead, every wall, column, ceiling, staircase, and roof was carved from the living volcanic bedrock itself, transforming the site into one of the world's largest collections of monolithic architecture. The greatest mystery begins with the extraordinary method of construction. Most monumental buildings become stable because thousands of individual stones distribute weight through carefully designed joints and foundations. Lalibela follows none of those principles. The builders first isolated enormous blocks of volcanic tuff by excavating deep trenches from the surface downward, in some places more than 12 meters deep, before hollowing out the interior of each remaining stone mass. Churches such as Bete Georgis stand entirely below the surrounding ground level, measuring approximately 12 meters in height, while remaining connected to the mountain by only the uncut bedrock beneath them. Every doorway, window, pillar, and vaulted ceiling was carved only after the surrounding rock had already been removed. A single major error during excavation could have transferred stress unevenly through the remaining stone, potentially fracturing the entire monument long before completion. Yet nearly 800 years later, the overall geometry remains remarkably intact despite centuries of weathering. That achievement becomes even more remarkable once the structural consequences of excavation are considered. Creating the interior chambers required removing an estimated 60 to 70% of the original rock volume within each isolated block. Every ceiling therefore functions as a natural rock span carrying thousands of tons of overlying material. Modern rock engineering demonstrates that the stability of such excavations depends on precise relationships between span width, roof thickness, fracture orientation, and the compressive strength of the host rock. Volcanic tuff generally possesses compressive strengths ranging from roughly 10 to more than 40 megapascals, depending on density and alteration, substantially weaker than granite. Excavating large, unsupported chambers inside such material without triggering progressive collapse normally requires detailed knowledge of stress distribution. No construction drawings, measurement systems, or engineering manuals explaining how medieval Ethiopian builders determined these safe proportions have ever been discovered. The choice of geological formation may itself represent one of the site's least understood technical accomplishments. Lalibela was carved into volcanic tuff, produced by ancient eruptions across the Ethiopian highlands. Freshly exposed tuff is significantly softer than crystalline igneous rocks, allowing iron tools to remove material more efficiently. However, prolonged exposure often hardens the outer surface through dehydration, mineral alteration, and the gradual development of protective weathering crusts. Selecting the correct horizon within these volcanic deposits would have been critical because neighboring layers frequently differ in grain size, cementation, porosity, and fracture density, despite appearing visually similar. A slightly weaker layer could have developed extensive cracking once enormous quantities of surrounding rock were removed. Geological mapping indicates that the churches occupy comparatively competent sections of the volcanic sequence, yet no historical evidence explains how medieval builders identified these stable horizons without modern geological investigation. As excavation continued deeper below the original ground surface, another threat became unavoidable. Water has destroyed countless rock-cut monuments throughout history, because infiltration gradually enlarges fractures, weakens mineral bonds, and accelerates erosion. Lalibela nevertheless incorporates an extensive drainage system carved directly into the bedrock itself. Channels, trenches, collection basins, and sloping passages guide seasonal rainfall away from the monuments before prolonged saturation can occur. Ethiopia's northern highlands experience highly seasonal precipitation, with annual rainfall commonly ranging between approximately 700 and over 1,000 millimeters, depending on elevation and local climate. Without effective drainage, repeated wetting and drying cycles over hundreds of years would likely have produced widespread structural deterioration. Instead, much of the hydraulic network continues to function, suggesting that water management formed an integral part of the original engineering rather than a later modification. The underground network surrounding the churches presents another unresolved engineering challenge. Narrow corridors, stairways, ceremonial passages, and tunnels connect many structures beneath the surface, often passing surprisingly close to the foundations of neighboring monuments. Every additional excavation altered the stress field within the surrounding rock mass. Modern tunnel construction relies upon geological surveys, stress modeling, and continuous monitoring because even small changes in excavation geometry can initiate unstable crack propagation. The builders of Lalibela created an interconnected subterranean landscape while leaving sufficient rock between adjacent excavations to preserve long-term stability. Archaeologists can document the finished network with three-dimensional laser scanning, but no surviving evidence reveals how its designers anticipated the structural consequences before removing the rock. The remarkable geometric precision visible throughout the complex raises equally difficult questions. Exterior walls extending more than 10 meters remain strikingly straight, corners approach accurate right angles, and decorative windows maintain consistent symmetry despite being carved from the top downward. Unlike masonry construction, where individual blocks can be replaced or adjusted during assembly, subtractive excavation offers almost no opportunity to correct significant mistakes. Removing only a few centimeters too much material from a structural corner or support pillar would permanently weaken the entire monument. Modern digital surveys continue to demonstrate impressive dimensional consistency across multiple churches, implying careful planning before excavation began. Yet the practical methods used to transfer measurements through deep vertical excavations remain undocumented. Perhaps the most overlooked mystery involves the immense quantity of rock that disappeared during construction. Excavating 11 monolithic churches, surrounding courtyards, connecting trenches, tunnels, and drainage channels required removing hundreds of thousands of cubic meters of volcanic material. This represents several 100,000 metric tons of rock, depending on the density of the individual tuff layers. Surprisingly little physical evidence identifies where this enormous volume was deposited. No comparable spoil fields survive nearby, and no written sources describe how such quantities of excavated material were transported across the rugged highland landscape. Whether the stone was reused locally, gradually dispersed through centuries of erosion, or systematically removed by methods now lost, remains uncertain. The absence of construction evidence deepens the puzzle even further. Monumental projects elsewhere in the ancient and medieval world commonly leave behind workshops, abandoned tools, unfinished stone blocks, workers' settlements, or administrative records documenting logistics and labor organization. Lalibela preserves remarkably little of this supporting infrastructure. Archaeologists know the churches were almost certainly commissioned during the reign traditionally associated with King Gebre Meskel Lalibela in the late 12th and early 13th centuries. Yet the technical organization behind one of Africa's greatest rock-cut architectural achievements remains largely invisible. The monuments themselves survive, but the engineering knowledge that made them possible appears to have vanished almost completely. Termessos rises more than 1,000 meters above sea level inside the Taurus Mountains, near modern Antalya, in southwestern Turkey, where an entire ancient city still clings to steep limestone slopes that geology suggests should have become progressively unstable long ago. Unlike many ancient mountain settlements that vanished beneath landslides or dense vegetation, Termessos was never completely forgotten, but its remarkable engineering was only properly understood after systematic archaeological surveys during the 20th century, followed by geological mapping, laser scanning, structural analysis, and detailed studies within Guluk Mountain National Park. Founded by the Pisidians and flourishing from at least the 4th century BCE before later becoming part of the Hellenistic and Roman worlds, the city occupies an elevation of roughly 1,000 to 1,200 meters across an exceptionally rugged karst landscape. Ancient writers, including Arrian, recorded that even Alexander the Great abandoned plans to capture the city in 333 BCE because its natural defenses made a direct assault almost impossible. Yet the military reputation of Termessos is only part of a much deeper mystery. The greater question is how an entire urban center was successfully constructed on terrain that modern engineers would normally regard as one of the least favorable places for large-scale permanent architecture. Every surviving structure seems to demonstrate an extraordinary understanding of the mountain itself, rather than an attempt to overpower it. Instead of leveling the landscape, the builders carved enormous terraces directly into fractured limestone, allowing each major public building to rest upon carefully selected sections of exposed bedrock. Modern geological investigations show that the Taurus Mountains consist largely of heavily jointed Mesozoic limestone, affected by tectonic uplift, solution cavities, and countless natural fractures. Such terrain normally creates significant instability because water penetrates cracks, gradually enlarges voids through chemical weathering, and weakens entire rock masses over centuries. Constructing a city weighing many thousands of tons across these conditions without triggering progressive slope failure, would require detailed knowledge of rock stability, yet no surviving inscriptions, engineering manuals, or construction records explain how the Pisidians identified which parts of the mountain could safely support temples, marketplaces, houses, reservoirs, and defensive walls. Even today, geotechnical engineers rely upon drilling, seismic surveys, and laboratory testing before approving large projects on comparable slopes, whereas the ancient builders somehow reached remarkably accurate decisions using techniques that remain undocumented. This unexplained precision becomes even more striking inside the theatre, perhaps the most dramatic monument at Termessos. Rather than occupying a broad plateau, the theatre sits directly against the mountainside while overlooking distant valleys far below. Much of its seating depends upon the natural rock instead of massive artificial substructures, reducing weight while allowing the mountain itself to carry the greatest structural loads. Although earthquakes have repeatedly affected southwestern Anatolia throughout recorded history, numerous seating rows remain closely aligned after more than 2,000 years. Structural researchers have suggested that selecting exceptionally competent rock masses instead of merely convenient locations may have been one of the city's greatest engineering achievements, but no one knows how such assessments were consistently made across the entire settlement without modern geological instruments. The more archaeologists examine the city's layout, the more its retaining systems challenge conventional expectations. Nearly every major terrace depends upon stone retaining walls, holding back enormous volumes of soil and rock on steep inclines, where gravity constantly attempts to pull everything downhill. Ordinarily, retaining walls gradually fail because rainwater accumulates behind them, increasing hydrostatic pressure until the masonry bulges or collapses. Yet many of Termessos' terrace walls remain standing after more than 20 centuries, despite continuous seasonal rainfall, winter freeze-thaw cycles, tree root expansion, and repeated seismic activity. Excavations have revealed carefully positioned drainage channels, stone-lined outlets, and subtle gradients that appear designed to remove infiltrating water before dangerous pressure could develop. Some specialists believe much of the drainage network remains buried beneath accumulated sediments, meaning the city may still conceal an integrated hydraulic system that has never been fully mapped. Water management presents another puzzle because the mountain offers no major river capable of sustaining a large permanent population. Instead of depending upon abundant natural springs, the inhabitants constructed numerous cisterns carved directly into bedrock, many coated with waterproof hydraulic mortar, whose exact performance continues to attract scientific attention. Rainwater flowing naturally across the mountain appears to have been intercepted, filtered, and stored with remarkable efficiency. Laboratory analysis has shown that several surviving waterproof mortars contain carefully proportioned mixtures of lime, crushed ceramics, and mineral aggregates capable of resisting water penetration for extraordinarily long periods. Although similar hydraulic technologies were known elsewhere in the ancient Mediterranean, archaeologists still debate how builders working in such an isolated mountain environment consistently produced durable reservoirs capable of surviving centuries of climatic extremes without widespread structural failure. Even the streets contribute to the engineering mystery. Rather than forcing straight avenues across impossible gradients, the urban plan follows the mountain's natural contours with subtle adjustments that minimize excavation while reducing long-term erosion. Modern topographic surveys indicate that many roads, stairways, and public spaces align with naturally stable ridges instead of crossing zones more susceptible to collapse. This suggests the city's planners possessed an unusually sophisticated understanding of terrain stability achieved entirely through observation and practical experience. Their choices reduced the need for excessive retaining structures, while distributing structural loads across stronger portions of the landscape, creating a settlement that appears almost woven into the mountain rather than simply placed upon it. Time itself should have finished what gravity could not. Southwestern Turkey lies within a tectonically active region influenced by the complex interaction of the African, Arabian, and Anatolian plates, and historical records describe destructive earthquakes affecting nearby cities across many centuries. Geological weathering continuously enlarges fractures within limestone, while freeze-thaw expansion gradually widens existing cracks and weakens exposed rock surfaces. Under such conditions, large mountain settlements usually experience progressive deformation, collapsing terraces, displaced foundations, and widespread structural instability. Yet substantial portions of Termessos continue to occupy their original positions with surprising integrity. Although some buildings undoubtedly suffered damage and parts of the city were eventually abandoned, the overall urban framework still demonstrates a level of resilience that appears disproportionate to the hostile geological environment in which it was created. The first mistake would have brought the entire mountain down, long before the first statue appeared, before halls, pillars, or stairways emerged from the cliff. The builders of Kailasa Temple committed themselves to a construction method that offered no second chance. Instead of assembling stone block by block, they selected a single mass of volcanic basalt and began cutting downward from its summit, removing everything that was not part of the monument itself. More than 12 centuries later, the greatest mystery is no longer who commissioned the temple, but how a structure carved from the heart of a mountain continues to stand with remarkable structural stability after centuries of monsoon rainfall, weathering, and regional earthquakes, despite engineering choices that would appear extraordinarily risky even by modern standards. Kailasa Temple forms Cave 16 of the Ellora Caves, located in Maharashtra in western India, approximately 30 kilometers northwest of Aurangabad. Although the caves had never completely disappeared from local knowledge, their architectural significance only became fully understood through systematic surveys conducted during the 19th century, followed by archaeological investigations by the Archaeological Survey of India, geological mapping of the Deccan Traps, laser documentation, three-dimensional scanning, and structural studies over the last several decades. Most researchers attribute the construction of Kailasa to the reign of Rashtrakuta King Krishna I during the 8th century CE, while inscriptions and stylistic evidence suggest that later rulers continued expanding decorative elements. Yet historical records explain remarkably little about the engineering process itself, leaving the monument to answer questions through its surviving stone rather than written documentation. Unlike almost every monumental building of the ancient world, Kailasa was never assembled. It was revealed. Engineers first isolated a massive rectangular block by excavating deep trenches around its perimeter, before gradually carving downward toward the base. Modern estimates suggest that between 200,000 and 400,000 metric tons of basalt were removed, although some calculations propose even larger volumes, depending on how unfinished surrounding excavations are interpreted. Regardless of the exact figure, the scale immediately presents a logistical puzzle. Every fragment of stone had to be detached, broken into manageable pieces, transported out of the excavation, and discarded without damaging the portions intended to remain. Archaeologists have never identified spoil deposits large enough to account conclusively for all of the removed material. And while it is entirely possible that the stone was reused over centuries for roads, settlements, or smaller construction projects, the absence of a clearly identifiable disposal system remains one of the site's enduring unanswered questions. The deeper researchers examine the monument, the more remarkable its sequence of construction becomes. Builders could not gradually adjust the design as work progressed, because the roof had to be completed before the lower levels even existed. Every corridor, column, shrine, staircase, and courtyard depended upon calculations made long before those features became visible. Removing too much rock at any stage would permanently weaken the structure, while leaving excessive material would make later excavation impossible without altering the intended geometry. Modern construction projects often rely upon continuous measurements, structural modeling, and corrective modifications throughout the building process. Yet Kailasa presents surprisingly little archaeological evidence for major design revisions. There are unfinished carvings and abandoned decorative details, but there is no indication that the primary structural framework required large-scale correction after excavation had begun. This unusual construction method naturally leads to an even more difficult engineering question. The temple is not simply carved into a mountain. Much of the mountain itself has been hollowed away, while preserving carefully positioned masses of rock that continue carrying the weight above them. Inside the complex, enormous halls open beneath ceilings, supported by monolithic columns that were never transported or assembled. Each pillar is simply the portion of the original mountain left standing after everything surrounding it was removed. Structural engineers understand that columns function only when their dimensions correspond closely to the loads they support. If too much material is removed, stress concentrations increase dramatically, and fractures may begin propagating through the surrounding rock. Yet after approximately 12 centuries, most of these columns remain capable of supporting their original loads, with surprisingly limited evidence of catastrophic structural failure. This durability becomes even more impressive when viewed through the geology of the region. Kailasa is carved into the Deccan Traps, one of Earth's largest volcanic provinces, created by immense lava eruptions near the end of the Cretaceous period, around 66 million years ago. Basalt is generally strong under compression, often exceeding 100 megapascals in compressive strength, depending on mineral composition and weathering, but it is rarely perfectly uniform. Cooling lava naturally develops joints, fractures, and variations in crystal structure that can become planes of weakness. Excavating a monument of this scale without accidentally exposing unstable fracture networks would have required exceptional understanding of the rock mass. Modern geological surveys identify multiple lava flows throughout the Deccan sequence, each possessing different mechanical characteristics, yet no surviving text explains how ancient builders evaluated these differences before beginning excavation. That uncertainty extends to the remarkable geometric precision visible throughout the monument. Because excavation proceeded downward rather than upward, surveyors had no opportunity to observe the completed structure from a distance while work remained underway. Once the upper levels had been cut, every measurement needed to be transferred vertically into deeper sections with sufficient accuracy to preserve symmetry across courtyards, bridges, shrines, and galleries extending over several stories. Researchers have proposed combinations of plumb lines, measuring chords, grids, and reference shafts, all of which were known in ancient India, but no archaeological evidence identifies the exact surveying system employed at Kailasa. The finished monument nevertheless maintains alignments that would have demanded consistent precision throughout decades of excavation. Bridges connecting elevated sections introduce another structural paradox. Unlike conventional bridges assembled from separate components, these passages remain continuous parts of the original bedrock. To create them, workers first removed every supporting mass beneath, while leaving only the narrow volume intended to function as the bridge itself. Any miscalculation could have concentrated stress beyond the strength of the basalt. Yet, many of these elevated connections continue spanning open spaces after more than a millennium of environmental exposure. Their survival suggests that excavation followed an organized structural logic rather than decorative ambition alone. Water presented another threat, that could have gradually destroyed the monument long after construction ended. Heavy monsoon rains repeatedly strike western India, and standing water trapped within excavated courtyards would accelerate erosion, enlarge natural fractures, and weaken foundations over centuries. Instead, Kailasa incorporates carefully carved drainage channels, sloped surfaces, gutters, and runoff paths integrated directly into the surrounding rock. Many of these systems still guide rainwater away from vulnerable areas, reducing long-term deterioration despite centuries without modern maintenance. Their effectiveness indicates that hydrological planning formed part of the original design instead of being added after problems appeared. The sculptural program reveals another level of technical achievement, often overshadowed by the monument's size. Thousands of reliefs depicting deities, mythological narratives, animals, and architectural ornament were carved directly into basalt after the primary excavation had already established the structural framework. Basalt typically measures around 6 on the Mohs hardness scale, making detailed carving significantly more demanding than softer sedimentary rocks commonly used elsewhere in the ancient world. Every chisel strike removed material that could never be replaced. An accidental fracture extending into a supporting wall or column would have compromised both artistic and structural integrity simultaneously. Nevertheless, many carvings preserve extraordinary detail despite prolonged exposure to humidity, biological growth, and surface weathering. Kailasa's durability is evident in its resistance to earthquakes. Despite frequent seismic activity in western India, the temple has avoided major structural collapse. Its connection to the surrounding bedrock helps distribute seismic forces, while the careful placement of columns and remaining rock mass contributes to its long-term stability. Constantine's bridge once crossed the Danube between the Roman cities of Oescus in present-day northern Bulgaria and Suceava in southern Romania. And although almost nothing remains visible today, its true scale only emerged through archaeological excavations at both bridgeheads, 19th-century topographic surveys, aerial photography, underwater investigations, geomorphological studies, and analyses of late Roman historical sources. Dedicated in AD 328 during the reign of Emperor Constantine the Great, the bridge measured approximately 2.4 kilometers in total length, with more than 1 kilometer spanning the active channel of the Danube itself, making it one of the longest river bridges ever constructed by the Roman Empire. Yet the greatest puzzle is not how impressive it appeared in antiquity, but how Roman engineers managed to build a structure across one of Europe's most unpredictable rivers using techniques whose most critical details have almost completely disappeared from the archaeological record. The mystery begins beneath the river rather than above it, because every large bridge ultimately depends on foundations that cannot be seen. Modern engineers understand that the Danube presents an exceptionally difficult environment for construction. Depending on the season, the river can exceed 1 kilometer in width, while powerful currents continuously transport enormous quantities of sand, gravel, and sediment that reshape the riverbed over time. Seasonal flooding dramatically increases hydraulic pressure, and winter ice can exert tremendous horizontal forces against bridge piers. Today, projects across comparable rivers rely on steel sheet piling, reinforced concrete caissons, heavy dredging equipment, hydraulic pumps, and computer simulations before construction even begins. Constantine's bridge, however, was completed almost 17 centuries before any of those technologies existed, leaving historians with a question that still lacks a definitive answer. How were its foundations placed deeply enough to survive such conditions? Excavations around Oescus and Suceava have revealed substantial masonry abutments and associated defensive structures. confirming that the bridge formed part of an integrated military and transportation network rather than an isolated monument. What archaeologists have not recovered is equally significant. The central foundations that once supported the bridge across the deepest sections of the river have either been destroyed, buried beneath later sediment, or remain inaccessible beneath the modern Danube. Without those foundations, researchers cannot directly determine the dimensions of the cofferdams, the depth of the piles, the arrangement of the stone cores, or the precise construction sequence. Much of what is written about the engineering therefore depends on comparisons with other Roman bridges instead of direct evidence from Constantine's bridge itself, leaving one of its most important technological achievements effectively hidden beneath the river. This uncertainty becomes even more remarkable when considering the behavior of the Danube over long periods of time. Rivers of this scale are dynamic geological systems rather than stable channels. Satellite observations, sedimentological studies, and historical mapping demonstrate that major European rivers gradually migrate across their floodplains as erosion removes material from one bank while deposition builds another. Even relatively small changes in current velocity can alter sediment transport enough to expose or bury foundations over centuries. Engineers designing modern bridges must therefore predict not only present conditions but also future river evolution. Roman surveyors obviously lacked satellite imagery, yet the location they selected remained functional long enough to justify one of the largest infrastructure investments of Constantine's reign. Whether they achieved this through generations of accumulated observation, sophisticated hydraulic knowledge, or practical experimentation remains uncertain because the technical documents that might explain their methods have not survived. Any discussion of the bridge inevitably leads to the problem of underwater construction. Most historians believe Roman engineers employed cofferdams, temporary watertight enclosures formed by driving timber piles into the riverbed before pumping out the enclosed water to expose dry working conditions. Ancient authors describe similar techniques elsewhere in the Roman world, but no surviving account explains exactly how they were adapted for a river as broad and forceful as the Danube. Building a cofferdam is relatively straightforward in calm water, yet maintaining one against continuous current, fluctuating water levels, floating debris, and seasonal floods represents a far greater challenge. Every additional meter of water depth increases hydrostatic pressure, while any small structural weakness can rapidly lead to catastrophic failure. Since no intact Roman cofferdam has ever been discovered at Constantine's bridge, the precise engineering solution remains speculative despite decades of research. Closely connected to this mystery is the possible use of Roman hydraulic concrete. Scientific studies published during the last 2 decades have shown that Roman marine concrete often became stronger over time through chemical reactions between volcanic ash, lime, and seawater, producing durable mineral phases such as aluminous tobermorite and philipsite. Research led by geological and materials scientists has demonstrated that these crystalline structures can gradually reinforce the concrete instead of weakening it, explaining the remarkable longevity of many Roman harbors. Whether the same technology played a significant role beneath Constantine's bridge is still unknown because too little original material has survived for detailed laboratory analysis. If hydraulic concrete was extensively employed beneath the foundations, it would explain part of the bridge's durability, but without physical samples, the hypothesis cannot be confirmed. The bridge also raises difficult questions about Roman structural design, because the surviving evidence suggests that its stone foundations supported a massive timber superstructure extending across the river. Timber may appear less durable than stone, yet it offers important engineering advantages for long-span bridges, by reducing weight and absorbing dynamic loads more effectively than rigid masonry alone. Even so, a wooden bridge exceeding 1 kilometer above a major river would have experienced constant thermal expansion, contraction, vibration from military traffic, wind loading, moisture variation, and biological decay. Every joint connecting beams, braces, and decking would have needed to accommodate movement without compromising overall stability. Unfortunately, wood rarely survives for more than a fraction of the bridge's age, unless preserved under exceptional environmental conditions, leaving almost nothing from which archaeologists can reconstruct the original structural system. The speed with which Constantine's bridge appears to have been completed presents another engineering puzzle. Historical sources indicate that the bridge was inaugurated in AD 328, only a short period after construction began. Although exact timelines remain debated, completing a project of this magnitude within only a few years would have required extraordinary logistical coordination. Tens of thousands of tons of stone had to be quarried, shaped, transported, and positioned. Vast quantities of timber were needed not only for the bridge itself but also for scaffolding, temporary works, cofferdams, lifting equipment, and worker facilities. Food, tools, animals, engineers, soldiers, and laborers all had to be supplied continuously along a frontier far from the empire's Mediterranean heartland. Yet almost none of the administrative records describing this enormous construction effort have survived, leaving modern historians to reconstruct the project indirectly from archaeology and scattered historical references. The choice of location itself remains surprisingly sophisticated. The Danube offers many crossing points, yet not every location provides stable geology beneath the riverbed. Successful bridge construction depends on bedrock depth, bank stability, current velocity, flood behavior, and access to transportation routes on both sides. Modern geotechnical investigations routinely involve drilling cores, seismic imaging, and computer modeling before selecting bridge alignments. Roman engineers possessed none of these technologies, yet Constantine's bridge successfully linked two strategically important military centers while integrating with roads, fortifications, and frontier defenses across the lower Danube. Whether this accuracy resulted from remarkable empirical surveying techniques or from generations of accumulated military experience remains impossible to determine, because the original surveying methods have vanished along with the bridge itself. Its disappearance is striking. Unlike Trajan's bridge, which left visible piers, Constantine's bridge survives only in scattered remains. Flooding, river shifts, dismantling, and erosion may explain this, but none fully accounts for the loss. The Danube has continually reshaped its channel, likely burying parts of the bridge deep beneath sediment, beyond current archaeological reach. Baalbek rises in Lebanon's Bekaa Valley, about 85 kilometers northeast of Beirut, where travelers documented its ruins for centuries before a German expedition carried out the first large systematic excavations between 1898 and 1903. Later architectural surveys, quarry excavations, and geological studies revealed that the Roman sanctuary of Heliopolis rested on one of the most extreme stone platforms attempted in antiquity. The complex developed mainly from the late 1st century BCE through the Roman imperial period, and the Temple of Jupiter once stood behind a court supported by columns nearly 20 meters high. Most of that upper structure has fallen, but the retaining system beneath it remains, creating Baalbek's central paradox: earthquakes, weathering, dismantling, and reuse destroyed much of the visible temple, while some of the heaviest masonry ever placed by ancient builders stayed locked into the terrace. The western wall contains the trilithon, 3 limestone blocks, each more than 19 meters long, roughly 4 meters high, and about 3.5 meters deep. Estimates usually place each block near 750 to 800 tons. They were not laid at ground level, but incorporated into an elevated course above another row of massive foundation stones. Their weight is only part of the problem, because a block approaching 800 tons could not be corrected easily once movement began. A small difference in the road surface, friction, or pulling force could make it twist, settle unevenly, or crush the equipment beneath it. Nevertheless, the 3 stones were aligned into a continuous horizontal course with close joints that allowed them to function as a single retaining band. The nearby quarry makes the scale even harder to explain. Located less than a kilometer from the sanctuary and slightly higher than the temple platform, it allowed engineers to use a generally descending route rather than lift the stones through the entire journey. This reduced the task but did not solve it, because controlling hundreds of tons downhill could be more dangerous than pulling the same load across level ground. Excavations by the German Archaeological Institute and Lebanese University exposed an unfinished monolith measuring approximately 19.6 meters by 6 meters by at least 5.5 meters. Its estimated mass is about 1,650 tons, making it one of the largest known blocks quarried in the ancient world. Other abandoned megaliths nearby show that the builders repeatedly tested the limestone bedrock, but the largest examples were never removed, perhaps because fractures, excessive mass, or difficult undercutting made transport impractical. These abandoned stones reveal both ambition and failure. Roman engineers possessed capstans, pulleys, timber sledges, rollers, cranes, earth ramps, and large labor forces, so no unknown machine is required in principle. The unresolved issue is the exact combination used at Baalbek. Ordinary treadwheel cranes could not simply suspend an 800-ton block, and no surviving ancient account describes the operation. One reconstruction uses a prepared earthen roadway, heavy sledges, multiple capstans, and coordinated teams. Another proposes that the terrace was built outward around the stones, meaning they were never lifted several meters through open air. Both fit known Roman engineering, yet neither has been confirmed by a surviving ramp, transport fittings, or a complete archaeological trail. The masonry adds another difficulty because enormous size does not make accurate construction easier. The contact beds had to be dressed across many square meters so that pressure would not concentrate on a few high points. Limestone is softer than granite and can be shaped with iron picks, chisels, saws, abrasives, and repeated checking, but an error across a 19-meter surface becomes difficult to correct after placement. Builders probably used straight edges, plumb bobs, sighting lines, water levels, and trial fitting. The stonework was not machine perfect everywhere, as popular claims often suggest, but it was controlled closely enough to distribute compression through blocks of extraordinary mass without mortar serving as a flexible bedding layer. That distribution of weight helps explain why the podium survived when much of the temple above it did not. Baalbek lies within the tectonically active Levant, influenced by the Dead Sea Transform fault system, and the sanctuary endured repeated earthquakes. The earthquakes of 1759 were especially destructive, reducing the surviving columns of the Temple of Jupiter from 9 to 6. Tall columns amplify lateral motion, their drums can shift, and the heavy stone above them creates dangerous bending and overturning forces. The retaining wall behaves differently. Its blocks are broad, deeply confined, loaded mainly in compression, and restrained by their own weight and surrounding masonry. Large contact areas create friction, while the low, massive geometry limits the leverage that causes slender structures to topple. Baalbek was not earthquake-proof. Sections collapsed, blocks shifted, and stone was reused in later fortifications. Its survival instead shows how the vulnerable height of the temple contrasted with the mass, confinement, and compression of the podium. The same seismic forces that overturned columns and dislodged their upper stonework were less effective against retaining blocks that had little height relative to their width and were trapped inside a much larger body of masonry. The platform survived not because it escaped destruction, but because its geometry forced most of its material to remain under compression, the condition in which limestone performs most reliably. The chronology of the two podia also remains debated. Differences in masonry once encouraged claims that the Trilithon predated Rome, but no secure evidence supports a lost prehistoric builder. Most specialists connect the terrace with the late Hellenistic or early Roman sanctuary, possibly within a unified monumental project begun near the establishment of the Roman colony in the late 1st century BCE, although its exact construction sequence and practical method remain uncertain. Archaeological research has therefore replaced theories of an unknown civilization with a more difficult historical question. Why did Roman planners choose a scale of stone construction rarely repeated elsewhere in their empire? One possibility is that the giant blocks reduced the number of vertical joints in the outer wall, creating long courses that resisted separation and spread pressure across a broad area. Their mass may also have increased friction between courses and stabilized the terrace against gradual settlement. However, this cannot fully explain why the builders selected blocks weighing several times more than the stones commonly used in other Roman temples. The sanctuary's religious importance, access to a suitable limestone quarry, the descending route, imperial resources, and the desire to create an unmatched ceremonial platform probably combined to make the project possible. But no surviving inscription records the calculations, machinery, labor organization, or sequence used to complete it. Trajan's bridge stood across the Danube between present-day Drobeta Târnu Severin in Romania and Kladovo in Serbia. Yet the first clues to how extraordinary it truly was emerged not from the surviving ruins above water, but from centuries of archaeological investigation beneath the river itself. Medieval travelers still described isolated stone piers rising from the current, while systematic excavations during the 19th and 20th centuries, followed by underwater archaeology, bathymetric mapping, aerial photography, LiDAR surveys, and structural analysis, gradually revealed that these remains belonged to what was once the longest bridge ever constructed in the ancient world. Built between AD 103 and 105 under Emperor Trajan, and designed by the renowned engineer Apollodorus of Damascus, the bridge stretched approximately 1,135 meters across one of Europe's largest rivers, supported by 20 massive masonry piers that carried a timber superstructure roughly 15 meters wide. Although only fragments survive today, the archaeological evidence immediately raises a question that becomes more difficult the deeper researchers investigate. How did Roman engineers build foundations capable of resisting the Danube for nearly 2,000 years, when many modern bridges require extensive reinforcement after only decades? The mystery begins with the river itself. Even today, the Danube remains one of Europe's most powerful waterways, carrying enormous seasonal variations in discharge that can exceed 10,000 cubic meters of water per second during major floods, while transporting vast quantities of sediment, drifting ice, and floating debris capable of damaging modern bridge piers. The section chosen for Trajan's bridge was nearly 1 kilometer wide, with an unstable riverbed composed of gravel, sand, and alluvial deposits constantly reshaped by changing currents. Modern hydraulic engineering recognizes scour around bridge foundations as one of the leading causes of bridge failure, because fast-moving water removes supporting sediments until heavy piers begin to settle or collapse. Yet underwater investigations have shown that several of Trajan's massive foundations remained remarkably stable long after the timber deck disappeared, suggesting that Roman surveyors possessed a far more sophisticated understanding of river hydraulics than surviving written sources can explain. That question becomes even more intriguing when attention turns to the construction process itself. Most historians believe Apollodorus relied on enormous timber cofferdams to isolate sections of the river so that foundations could be built in dry conditions. But no contemporary engineering manual describes exactly how these structures functioned on the Danube. Vitruvius discussed construction techniques for marine works more than a century earlier, yet he never described a project remotely comparable in scale. Archaeological remains indicate that each masonry pier measured roughly 38 meters long, about 19 meters wide, and nearly 44 meters high from foundation to deck level. Dimensions that would have required excavation far below the river surface, while resisting tremendous hydrostatic pressure. Engineers today can model possible cofferdam arrangements using computational fluid dynamics, but none fully explain how Roman builders prevented leakage, stabilized temporary walls against powerful currents, removed groundwater, or maintained safe working conditions over months of construction without modern pumps or steel sheet piling. The absence of detailed technical documentation has left one of antiquity's greatest engineering operations largely hidden behind educated reconstruction rather than direct evidence. As researchers examined the surviving masonry more closely, another puzzle emerged from the remarkable durability of the bridge's foundations. Unlike freestanding monuments exposed mainly to gravity, bridge piers must endure constant horizontal loading produced by water pressure, debris impacts, thermal expansion, and seasonal ice. Geological surveys suggest that the Danube has altered its channels repeatedly since Roman times, yet several foundations continued resisting erosion despite centuries of hydraulic attack. This resilience implies careful selection of foundation depth and placement before construction even began. Without sonar, drilling rigs, or modern geotechnical equipment, Roman engineers somehow identified locations capable of supporting thousands of tons of masonry while minimizing future scour. How they measured subsurface conditions beneath a fast-flowing river remains uncertain because no Roman text records procedures for underwater geological investigation on this scale. Material science has added another layer to the mystery. Roman concrete has become famous after laboratory studies revealed that volcanic ash mixed with lime produces durable calcium-aluminum silicate hydrates and minerals such as aluminous tobamorite, compounds capable of strengthening concrete through long-term interaction with water. Similar mechanisms have been identified in Roman harbor structures that have survived marine environments for over 2 millennia. Whether identical hydraulic concrete mixtures were employed extensively within Trajan's bridge foundations remains debated, because the Danube lies hundreds of kilometers from the principal volcanic ash deposits around the Bay of Naples, traditionally associated with high-quality pozzolana. Some researchers argue that volcanic materials were transported over extraordinary distances through the Roman logistical network, while others propose that local mineral sources, or alternative aggregate compositions, achieved comparable performance. The exact formulation used beneath the river has never been conclusively established, leaving unanswered questions about how the bridge acquired such exceptional longevity. These uncertainties become even greater when considering the logistics required to assemble the structure. Estimates suggest that constructing 20 enormous piers demanded tens of thousands of dressed stone blocks, immense quantities of mortar, timber, iron clamps, and specialized lifting equipment, all delivered to an active military frontier during Trajan's Dacian campaigns. Reliefs on Trajan's column depict cranes, ships, and construction activity, but they provide only symbolic snapshots rather than detailed engineering drawings. No surviving blueprint explains how stones weighing several tons were positioned with sufficient precision inside confined cofferdams, while currents continuously pressed against temporary retaining walls. Experimental archaeologists have demonstrated that Roman treadwheel cranes could lift impressive loads, yet coordinating dozens of heavy lifts simultaneously across a river nearly 1 kilometer wide would have required planning on a scale unmatched anywhere else in the ancient world. Attention then shifts upward to the timber superstructure, another aspect that challenges conventional expectations. Ancient sources, including Cassius Dio, indicate that wooden arches or beams connected the masonry piers, creating a crossing capable of supporting the rapid movement of Roman legions into Dacia. Individual spans were approximately 50 meters long, extraordinary distances for timber construction before industrial engineering. Wood naturally expands, contracts, absorbs moisture, and gradually deteriorates under repeated loading, especially in climates with freezing winters and hot summers. Roman carpenters undoubtedly possessed remarkable woodworking skills, yet the precise structural system allowing repeated military traffic across such long spans has disappeared completely because the timber was dismantled, probably during the reign of Hadrian, after the Dacian Wars had ended. As a result, historians understand the stone supports far better than the bridge deck they once carried.